At the smallest scales ever explored, matter no longer behaves in the quiet, predictable way everyday experience would suggest. Outcomes refuse to settle into single answers. Properties appear only through interaction. Patterns emerge that follow clear rules, yet resist simple cause and effect. What seems stable from a distance becomes fluid up close, guided less by certainty than by tendency. Welcome to the Sleepy Scientist. If you enjoy drifting through questions that lie far beneath everyday experience, you're very welcome to settle in and let these quiet explorations unfold. And if you feel like it, share where in the world you are listening from tonight. It is always comforting to know how far these thoughts travel. At these deeper levels of reality, familiar expectations loosen without effort. The solid world suggested by touch and sight softens into something less definite. Certainty thins. Location becomes approximate. Motion no longer traces clean paths, but spreads into ranges of possibility. Even the idea of an object existing entirely on its own begins to blur, its boundaries losing the sharpness they seem to hold at everyday scales. For more than a century, physicists have explored this subtle territory, with instruments built for extraordinary sensitivity, detectors capable of registering individual particles of light, systems cooled until motion nearly disappears, mathematical descriptions refined again and again, not to satisfy intuition, but to remain faithful to what experiments consistently reveal. What has emerged is not disorder, but a different kind of structure, one that resists everyday logic, yet proves remarkably dependable. Predictions confirmed with extraordinary precision, technologies built upon principles that feel counterintuitive, yet perform their roles quietly and without fail. Laboratories and research institutions around the world continue to refine this picture, extending measurement, increasing control, and probing ever more delicate regimes. With each improvement, the view grows clearer, even as its deeper implications become more subtle rather than more certain. This journey moves slowly through that landscape, not to force conclusions and not to simplify what resists simplicity, but to trace the shape of quantum reality with care, to understand what can be known, what can be measured, and where certainty naturally gives way to probability. Settle in. Let the smallest structures unfold quietly. Human intuition is a remarkable tool, but it is also a deeply specialized one. It was shaped slowly over hundreds of thousands of years to help small groups of humans survive in a narrow band of environments. It helps judge distance well enough to throw a stone. It estimates speed accurately enough to avoid a falling branch. It senses cause and effect clearly when one solid object strikes another. What it was never designed to do is describe the behavior of reality at scales far smaller than anything a human body can interact with directly. The brain builds its expectations from experience. From childhood onward, the world appears solid, continuous, and stable. Objects remain where they are unless something pushes them. Motion follows smooth paths. Causes precede effects in a tidy sequence. These patterns are reinforced millions of times over a lifetime until they feel not just familiar, but inevitable. It is hardly surprising, then, that when physics reveals a domain where these expectations no longer hold, the reaction is discomfort rather than curiosity. At very small scales, intuition begins to mislead almost immediately. The idea that an object must always be somewhere specific feels obvious, yet nature does not seem obligated to honour that expectation. The assumption that things move along clear trajectories works beautifully for planets and projectiles, but quietly fails for electrons and photons. This failure does not arise because the universe becomes chaotic or poorly behaved. It arises because intuition was never built to operate there in the first place. Evolutionary biology offers a useful lens here. Natural selection rewards traits that improve survival and reproduction, not traits that reveal fundamental truth. A mind that accurately predicts the motion of prey across a savanna has a clear advantage. A mind that understands probability distributions at atomic scales does not. As a result, the nervous system prioritizes speed, efficiency, and usefulness over precision or completeness. It compresses reality into simplified models that work well enough at human scale, and it discards the rest. Vision itself provides a simple example. Human eyes respond to a narrow slice of electromagnetic radiation, ignoring most of what exists. Hearing detects vibrations within a limited range, filtering out everything beyond it. Touch averages over countless microscopic interactions to produce the sensation of a smooth surface. None of these senses report reality as it truly is in detail. They report a practical summary. Quantum physics operates far below this summary, in a region where the shortcuts taken by perception no longer apply. Because of this, quantum behavior feels strange, not because it is illogical, but because it refuses to conform to expectations that were never meant to describe it. When experiments show that outcomes can only be predicted probabilistically, this clashes with the deeply ingrained belief that the world must unfold in a single, definite way. When particles behave like waves in some situations and like particles in others, it feels like a contradiction, even though it is a consistent description supported by repeated observation. Physics advances precisely by recognizing when intuition has reached its limit. History shows this pattern clearly. Classical mechanics once seemed complete, explaining the motion of objects from falling apples to orbiting planets. Yet as measurements became more precise, small discrepancies appeared. These were not failures of experimentation, but signals that familiar concepts were being stretched beyond their domain of usefulness. In the early years of the 20th century, this tension became impossible to ignore. Experiments probing heat radiation, atomic structure, and the behavior of light produced results that simply refused to fit existing frameworks. Scientists trained in classical thinking found themselves confronted with data that demanded something new. The discomfort was not subtle. Many of the figures who would later become associated with quantum theory expressed open frustration with its implications. Max Planck, whose work on radiation laid crucial groundwork, initially regarded his own contribution as a mathematical trick rather than a statement about nature. Albert Einstein, despite explaining the photoelectric effect, spent much of his later career uneasy with the probabilistic interpretation that followed. Even those who helped build the theory struggled with its meaning. Confusion was not a sign of incompetence. It was the natural response of human intuition meeting a regime it was never built to navigate. What is often overlooked is how carefully this confusion was handled. Quantum theory did not emerge from speculation or philosophical preference. It emerged because experiments left no alternative. Repeated measurements, carried out in laboratories across Europe and later around the world, produced consistent results that defied classical explanation. The theory grew not by abandoning logic, but by redefining what logic needed to account for. This distinction matters. There is a common temptation to treat quantum physics as evidence that reality is fundamentally irrational. In truth, it is extraordinarily disciplined. Its predictions are among the most accurate ever produced by science. Devices built upon quantum principles operate with astonishing reliability, from the timing systems used in global navigation to the electronics that quietly manage modern life. Strangeness does not imply instability, it simply signals unfamiliar structure. Accepting this requires a gentle adjustment of expectations. Instead of asking why quantum behavior does not make intuitive sense, it becomes more useful to ask why intuition should be trusted there at all. Just as eyesight cannot reveal ultraviolet light without assistance, intuition cannot reveal atomic behavior without guidance. Instruments extend the senses. Mathematics extends reasoning. Together they allow access to domains that would otherwise remain inaccessible. This process can feel unsettling at first, particularly when long-held assumptions are loosened. Yet it is also deeply human. Science progresses by recognizing the limits of what feels obvious and allowing evidence to lead the way. Each time intuition falters, it opens space for a deeper understanding to form, one that is less tied to immediate experience and more closely aligned with how nature actually behaves. There is a quiet reassurance in this. The universe does not change its rules depending on whether they feel comfortable. It behaves consistently, patiently, and without regard for expectation. When intuition fails, it is not a sign that reality is broken. It is a reminder that understanding is a skill that must be extended, not a sense that arrives fully formed. By softening resistance early, it becomes possible to approach unfamiliar ideas without tension. Confusion no longer feels like a problem to be solved quickly, but a natural stage in learning something genuinely new. The discomfort fades, replaced by curiosity. And with curiosity comes the willingness to let evidence speak, even when it whispers something unexpected. From this perspective, the limits of human intuition are not obstacles. They are signposts. They mark the boundary where everyday experience ends and deeper structure begins. Beyond that boundary lies not chaos, but a quieter, subtler order, waiting to be understood on its own terms. Touch feels convincing. A table resists pressure. A stone carries weight. Walls do their job reliably. From the moment hands can grasp objects, the world presents itself as firm and continuous, built from solid pieces pressed tightly together. This impression is reinforced every day, so consistently that it rarely invites question. Matter feels compact because it behaves that way at human scale. Yet when examined more closely, that confidence begins to dissolve. At the level of atoms, solidity fades into something far more delicate. An atom is not a miniature solid object, packed tightly with material. It is mostly space, vast amounts of it, relative to the tiny structures that define its presence. If an atom were enlarged to the size of a large cathedral, the central nucleus would be smaller than a grain of dust suspended at its centre. The rest would be empty volume, lightly occupied by a diffuse region where electrons are likely to be found, but rarely pinned to a precise location. This idea runs directly against intuition. Empty space is usually associated with absence, with nothingness. Yet atoms, despite being mostly empty, combine to form materials that feel unquestionably solid. The key lies not in how much space they contain, but in how they interact. Forces, not bulk, do the heavy lifting. Early models of the atom did not begin with this picture. For much of the 19th century, atoms were imagined as indivisible units, solid and featureless. They were useful bookkeeping tools for chemistry, not objects with internal structure. This began to change as experimental techniques improved and questions grew sharper. The assumption of indivisibility could not survive direct investigation. One of the most decisive moments came through experiments led by Ernest Rutherford in the early 1900s. By directing streams of charged particles toward thin sheets of gold foil, his team expected to see minor deflections, consistent with a soft, spread-out distribution of charge. Most particles passed straight through, as predicted, but a small fraction scattered sharply, some even rebounding backward. It was an outcome so unexpected that Rutherford famously likened it to firing a shell at tissue paper and having it bounce back. The implication was unavoidable. Atoms contained a tiny, dense core where most of their mass and positive charge resided. This nucleus occupied only a minute fraction of the atom's volume, yet exerted enough influence to dramatically redirect incoming particles. The rest of the atom had to be largely empty, offering little resistance. This discovery dismantled the idea of atoms as compact solids. It replaced it with a structure that was mostly absence, punctuated by a concentrated centre. The result was not a philosophical speculation, but a conclusion demanded by experimental evidence. Matter, it turned out, was already stranger than it appeared. Niels Bohr extended this emerging picture by proposing a model in which electrons occupied specific regions around the nucleus, associated with particular energies. While later refinements would replace simple orbital paths with probability distributions, Bohr's work provided a crucial stepping stone. It showed that atomic structure followed rules that were precise, constrained, and deeply unfamiliar to classical thinking. What is striking is how quickly this strange architecture proved reliable. Atomic models, once adjusted to reflect experimental reality, began to explain chemical behavior with remarkable accuracy. The periodic table gained deeper meaning. Spectral lines, once mysterious, became signatures of atomic structure. The emptiness within atoms did not make matter unstable, it made it understandable. So why does solid matter feel solid at all? The answer lies in interaction rather than occupancy. Electrons in one atom resist being pushed into the same states as electrons in another. Electromagnetic forces create strong repulsion at close distances. When a hand presses against a table, the sensation arises not because atoms touch like billiard balls, but because the electron clouds surrounding atoms resist compression. What feels like contact is actually a balance of forces. In this sense, solidity is an emergent sensation. It arises from countless interactions governed by underlying rules, not from material being packed edge to edge. The same principle explains why a metal bar supports weight while air does not, despite both being composed of atoms that are mostly empty. Structure, arrangement, and interaction matter far more than density alone. There is a subtle comfort in this realization. The world does not lose its reliability when examined closely. Chairs remain dependable, floors continue to hold. The emptiness within atoms does not undermine everyday experience. It simply reveals that experience is built atop deeper mechanisms, quietly doing their work without demanding attention. This perspective also serves as a concrete example of intuition meeting its limits. At human scale, assuming solidity works perfectly well. At atomic scale, it misleads. Neither view is wrong within its proper domain. Problems arise only when one is stretched beyond where it applies. Recognizing this makes it easier to accept that familiar concepts may need adjustment without being discarded entirely. There is gentle humour in how misleading appearances can be. A seemingly solid wall turns out to be a delicate arrangement of mostly empty atoms, held together by invisible forces behaving with unwavering consistency. It is not the sort of emptiness associated with fragility or collapse. It is structured emptiness, disciplined and reliable. Scientific bodies and laboratories around the world continue to refine this understanding, using increasingly precise instruments to probe atomic and subatomic structure. Particle accelerators, spectroscopy, and imaging techniques all confirm the same basic picture. Matter is stable not because it is filled, but because it is governed. By confronting the emptiness at the heart of matter, a deeper lesson quietly takes shape. Reality does not need to conform to how it appears in order to function beautifully. The assumption that matter must be compact and solid dissolves under scrutiny, replaced by a subtler and more elegant framework. One where space, force, and probability combine to produce the familiar world without ever quite becoming what intuition expects. Seen this way, the limits of intuition are no longer abstract. They are tangible. A solid object, resting calmly in a room, becomes a reminder that understanding deepens not by clinging to appearances, but by allowing evidence to reshape expectation. And once that reshaping begins, the strange quickly becomes coherent, even reassuring, on its own quiet terms. Energy feels smooth. A dimmer switch brightens a room gradually. A fire cools slowly as embers fade. Warmth seems to flow, not arrive in steps. This impression fits comfortably with everyday experience, where change appears continuous and divisible without limit. For a long time, physics assumed the same. Energy, it was thought, could be added or removed in any amount, however small. Nature, it seemed, had no preference for neat divisions. That assumption worked remarkably well for many problems. Classical physics described motion, heat, and light with impressive accuracy across a wide range of situations. Yet as measurements grew more precise toward the end of the 19th century, cracks began to appear. Certain experiments refused to behave as expected, no matter how carefully the calculations were adjusted. The smooth picture of energy began to fray at the edges. One of the most stubborn problems involved something deceptively ordinary: glowing objects. Any warm material emits light. As temperature rises, the colour and intensity of that glow change in predictable ways. This phenomenon, known as blackbody radiation, should have been straightforward to explain. Classical theories predicted how much energy should be emitted at different colours, assuming energy flowed continuously. They were wrong, spectacularly so. According to classical predictions, a hot object should emit infinite energy at high frequencies, producing an ever-increasing amount of ultraviolet light. This outcome, later nicknamed the ultraviolet catastrophe, was not a minor discrepancy. It was a complete failure. Real objects did not behave this way. Measurements showed that emitted energy rose to a peak and then declined smoothly, without any runaway explosion of ultraviolet radiation. The problem was not experimental error. Laboratories across Europe reproduced the same curves again and again. The failure lay in the underlying assumptions. Something about the way energy was being treated simply did not match reality. In 1900, Max Planck approached the problem with deep reluctance. He did not set out to overturn physics. His goal was to find a mathematical description that fit the data, nothing more. To do so, he introduced an idea he regarded as a formal trick rather than a statement about nature. He proposed that energy could only be exchanged in discrete amounts, proportional to the frequency of radiation. Instead of flowing smoothly, energy arrived in packets. At first, this proposal felt absurd even to its author. There was no intuitive reason energy should behave this way. Nothing in everyday experience suggested it. Planck himself hoped the assumption could later be discarded, leaving the equations intact. But the equations worked precisely because of that assumption, and without it, they failed entirely. This marked the quiet birth of quantization. Energy, it seemed, was not infinitely divisible. It came in fixed units, now known as quanta. These units were not arbitrary. Their size was set by a constant of nature, a number so small that its effects only become noticeable at microscopic scales. At human scale, the steps are tiny enough to appear smooth, much like individual grains of sand blending into a continuous beach. The significance of this shift is difficult to overstate. Quantization was not an interpretation layered onto existing theory. It was a structural rule forced into place by experimental evidence. The universe itself appeared to insist on it. Once introduced, the idea began to solve problems that had resisted explanation for years. Blackbody radiation curves matched observations perfectly. Heat capacity measurements at low temperatures began to make sense. The strange behaviour of a light and matter at small scale started to form a coherent pattern. What is striking is how conservative this revolution was. Planck did not announce a new worldview. He followed the data where it led, even when it led somewhere uncomfortable. Quantization emerged not from imagination, but from necessity. It was a reluctant conclusion, accepted because no alternative survived contact with experiment. This reluctance extended beyond Planck. Many physicists initially viewed quantization as a temporary patch, a clever fix awaiting deeper explanation. Yet, as time passed, the pattern repeated. Whenever classical assumptions were applied to atomic scale systems, predictions failed. Whenever energy was treated as coming in discrete amounts, predictions succeeded. Nature was consistent, even if the implications were unsettling. The idea of fixed energy exchanges deepened the departure from classical expectations already underway. Matter was no longer solid in the traditional sense. Now energy itself refused to behave as a smooth substance. Both insights pointed in the same direction. The familiar concepts that worked so well at large scales were becoming unreliable guides at small ones. There is a subtle elegance in this. Quantization introduces order, not chaos. By limiting the allowed energy values, it creates structure. Atomic stability depends on it. Without quantized energy levels, electrons would spiral unpredictably, atoms would collapse, and chemistry would dissolve into noise. The universe, as it turns out, relies on these tiny steps to remain coherent. Gentle humour can be found in how unintuitive this feels. A warm object does not emit heat in an endless drizzle, but in a disciplined sequence of microscopic drops. The steps are simply too small to notice without sensitive instruments. What seems continuous is often only continuous by approximation. Scientific institutions and laboratories worldwide have confirmed quantization through countless experiments. Spectroscopy reveals discrete lines where continuous bands were expected. Precision measurements of light and heat align perfectly with quantized models. Technology built upon these principles functions reliably every day, rarely drawing attention to the strange rules beneath its operation. Accepting quantization requires the same adjustment of intuition encountered before. Energy does not owe reality to familiarity. It follows its own rules, indifferent to whether they feel natural. Once this is accepted, confusion fades. What remains is a quieter appreciation for how deeply structured the universe is, even where it appears smooth. Quantization stands as the first unmistakable signal that classical expectations have reached their limit. It is the point where continuity gives way to discreteness, not as a philosophical statement, but as an experimentally enforced fact. From this foundation, the deeper architecture of quantum reality begins to take shape, one small step at a time, whether intuition approves or not. Light feels familiar. It illuminates rooms, warms skin, and reflects softly from surfaces without drawing attention to itself. For centuries, it was treated as a wave, spreading smoothly through space like ripples across water. This description worked beautifully. It explained reflection, refraction, interference, and diffraction with elegant precision. By the late 19th century, the wave theory of light was one of the great successes of classical physics, and yet, even as confidence grew, small experimental details began to whisper that something was missing. Waves, as they were understood, carried energy continuously. Increase the brightness, and more energy should arrive. Lower the brightness, and less should follow. Color or frequency should not fundamentally change how energy is delivered, only how it is distributed. These expectations seemed reasonable, grounded in experience and supported by maths. But when light interacted with matter at very small scales, those expectations quietly collapsed. One of the clearest examples came from experiments involving metal surfaces exposed to light. When certain metals were illuminated, electrons were ejected from their surface. This phenomenon, later called the photoelectric effect, had been observed before, but careful measurements revealed something deeply puzzling. The energy of the ejected electrons did not depend on how bright the light was. Instead, it depended on the colour. Below a certain frequency, no electrons were released at all, no matter how intense the light became. Increase the brightness as much as you like, and nothing happened. But raise the frequency just beyond a specific threshold, and electrons were ejected instantly, even when the light was faint. There was no gradual build-up, no delay. The effect appeared immediately. This behaviour made no sense within a purely wave-based description. If energy arrived continuously, brighter light should eventually free electrons regardless of colour. Experiments showed otherwise. The results were consistent, reproducible, and stubbornly resistant to classical explanation. In 1905, Albert Einstein provided a crucial insight. Building directly on the idea of energy quantization, he proposed that light sometimes behaves as if it arrives in discrete packets, each carrying a specific amount of energy tied to its frequency. If a single packet carried enough energy, it could eject an electron. If it did not, no amount of additional light would help, because the energy was not pooled. It arrived one packet at a time. This was not a philosophical claim about the nature of light. It was a physical explanation for observed behaviour, and it worked. The photoelectric effect followed naturally once light was treated as particulate in this specific context. What made this proposal so unsettling was not that light behaved like a particle, but that it did so only under certain conditions. In other experiments, light continued to display unmistakable wave-like behaviour. Interference patterns appeared. Diffraction spread beams into fringes. Reflection and refraction remained perfectly wave-like. There was no single description that fit all situations at once. This was not indecision on nature's part. It was consistency of a different kind. The behaviour of light depended on how it was interacting with the world. When spreading freely or passing through slits, wave descriptions captured its behaviour precisely. When exchanging energy with matter at small scales, particle-like descriptions became unavoidable. The same entity obeyed different rules depending on the context of interaction. This is often described as wave-particle duality, though the phrase can be misleading. It suggests that light switches identities, as if choosing between costumes. In reality, neither description is complete on its own. Waves and particles are human concepts, borrowed from familiar experience. Light does not commit to either. It simply behaves as experiments show it does. The photoelectric effect was not the only evidence pointing in this direction, but it was among the most decisive. It demonstrated that energy quantization was not limited to abstract radiation models. It applied directly to physical interactions. Light could deliver energy only in discrete amounts, and matter responded accordingly. Einstein himself viewed this as a provisional step rather than a final picture. He recognized its necessity, even while remaining uneasy with the broader implications that would follow. His contribution confirmed that quantization was not confined to theoretical convenience. It was embedded in how light and matter actually behave. This shift carried a deeper message. Classical categories were beginning to fail. Waves and particles, long treated as distinct kinds of objects, were no longer sufficient as fundamental descriptions. They remained useful approximations, but they could not be applied universally without contradiction. The lesson here is subtle but profound. Behaviour is not an intrinsic label attached to an object. It emerges from interaction. Light does not carry a fixed identity independent of circumstance. It reveals different aspects depending on what is being measured and how the measurement is ranged. There is a quiet elegance in this idea. Nature is not inconsistent. Human language is. The trouble arises when descriptions developed for one domain are forced onto another where they no longer apply cleanly. When that happens, confusion follows, not because reality is broken, but because expectations are misaligned. This understanding also builds naturally from energy quantization. If energy is exchanged in discrete amounts, then interactions must be described in ways that account for that discreteness. Waves alone cannot do this. Particles alone cannot capture interference. The deeper framework must accommodate both without reducing either to metaphor. Gentle humour often helps soften this transition. Light, it seems, refuses to settle into a single role. It behaves impeccably, just not according to the categories we would prefer. Like a guest who follows every rule of the house while ignoring the seating plan, it remains polite but unpredictable to the host. What matters is not how strange this feels, but how reliable it proves to be. Predictions based on this dual behaviour match experiments with extraordinary accuracy. Technologies that depend on light interacting with matter, from imaging systems to sensors, rely on these principles every day without incident. The rules may feel counterintuitive, but they are remarkably dependable. Scientific institutions around the world have tested and retested these ideas under countless conditions. The results remain consistent. Light does not misbehave. It simply does not conform to classical categories when those categories are applied too broadly. By accepting that behaviour depends on interaction, a great deal of tension dissolves. The need to force light into a single identity fades. What remains is a clearer view of how nature operates at small scales, guided by quantization and shaped by context. This marks another step away from classical expectations. Matter is not solid in the way it appears. Energy does not flow continuously. And light, perhaps most strikingly of all, refuses to be only one thing. It follows rules that are precise, experimentally grounded, and quietly indifferent to how comfortable they feel. Certainty feels reassuring. Drop a ball and it falls. Release a stone and it lands where expected. For centuries, physics reflected this comfort. Given enough information, the future could be calculated precisely. Positions led to velocities, velocities to trajectories, and trajectories to outcomes. The universe appeared to unfold like clockwork, each moment determined by the one before it. Quantum mechanics quietly breaks that expectation. At very small scales, even perfect knowledge of a system does not allow the prediction of a single definite outcome. Instead, it provides a range of possible results, each with a specific likelihood. Ask where a particle will be detected, and the answer is not a point but a distribution. Ask when an atom will emit light, and the response is not a schedule but a probability. This is not a limitation of measurement. It is how the theory itself is structured. This shift can feel deeply unsettling at first. Probability is often associated with ignorance. A coin toss is uncertain because the details of motion are too complex to track. Weather forecasts rely on probability because the atmosphere is chaotic. In these cases, probability stands in for missing information. If everything were known, certainty would return. Quantum mechanics does not work that way. Even in carefully controlled experiments, repeated under identical conditions, outcomes vary. The same preparation leads to different results, not because something was overlooked, but because variation is built into the fabric of the description. The theory does not say what will happen, it says what can happen and how likely each possibility is. This idea took time to settle into its modern form. Early formulations of quantum mechanics produced mathematical objects that behaved like waves, spreading through space and evolving smoothly over time. What those waves represented, however, was not immediately clear. They did not describe physical ripples like water waves. They were something else entirely. In the mid-1920s, Max Born offered a crucial interpretation. He proposed that these wave-like quantities did not represent matter itself, but probability. Specifically, they described the likelihood of finding a particle in a particular place if a measurement were made. The wave did not tell where the particle was. It told where the particle might be found. This was a profound conceptual step. It reframed the entire theory. The maths remained unchanged, but its meaning shifted. The smooth evolution of the wave described how probabilities evolved over time. When a measurement occurred, a single outcome appeared, selected from the range of possibilities according to those probabilities. Born's proposal was not philosophical decoration. It made direct contact with experiment. When physicists measured the distribution of particles hitting a screen, the results matched the predicted probability patterns with remarkable accuracy. Individual events were unpredictable. Large numbers of events produce stable, repeatable distributions. This distinction matters. Quantum probability is not vague or approximate, it is precise. Experiments involving electrons, photons, and atoms confirm predicted probabilities again and again, often to extraordinary levels of precision. When millions of particles are measured, the statistical patterns align perfectly with theoretical expectations. Uncertainty remains at the level of individual outcomes, not at the level of the overall structure. This precision is one reason probability in quantum mechanics should not be confused with randomness. Randomness implies a lack of pattern. Quantum systems display strong, reliable patterns, even while individual results remain unpredictable. The uncertainty lies not in the distribution, but in which member of that distribution will appear next. A helpful way to think about this is to reverse the usual intuition. In classical physics, certainty comes first, and probability enters only when information is incomplete. In quantum physics, probability comes first, and certainty appears only when many events are considered together. The order is inverted. This inversion reframes earlier ideas about wave and particle behavior. When light produces an interference pattern, it does so statistically. Individual photons arrive as discrete events, each striking a single point on a detector. Over time, a pattern emerges, not because each photon spreads out like a wave, but because the probabilities governing their arrival form a wave-like distribution. Seen this way, wave-particle duality becomes less puzzling. There's no need to imagine a single object switching identities. The wave describes probabilities. The particle describes outcomes. Both are essential, and neither alone tells the full story. This perspective also explains why quantum mechanics resists deterministic interpretation. The theory does not lack information about hidden variables waiting to be uncovered. Extensive experimental tests have shown that attempts to restore classical determinism fail. The probabilistic structure appears to be fundamental, not provisional. This was one of the most difficult aspects of quantum theory for many early physicists to accept. Albert Einstein famously objected to the idea that nature might be governed by chance, insisting that something deeper must be at work. Others shared his discomfort. Determinism had been a guiding principle for centuries, woven tightly into the identity of physics itself. Yet the evidence continued to point in the same direction. Experiments refined over decades supported Born's interpretation. Probability was not fading with improved measurement. It remained stubbornly central, no matter how carefully systems were prepared or how sensitive instruments became. There is a quiet elegance to this outcome. Probability does not weaken the predictive power of quantum mechanics. It defines it. The theory tells exactly how often each outcome will occur, even if it cannot say which one will occur next. In many applications, this is more than sufficient. Lasers, semiconductors, and atomic clocks all rely on quantum probabilities behaving exactly as predicted. Scientific institutions and laboratories around the world test these predictions daily, often without drawing attention to the deeper implications. Devices work because probabilities behave reliably. Engineers design systems confident that statistical outcomes will align with theory, and they do. Accepting probability as fundamental requires a gentle shift in expectation. The universe is not a machine that reveals its future one inevitable step at a time. It is a system that offers possibilities, constrained by precise rules and realized through interaction. Outcomes are not arbitrary. They are selected from a structured landscape of likelihood. There's even a certain kindness in this. Absolute determinism leaves no room for variation. Probability introduces flexibility without chaos. It allows systems to be stable on average while remaining open in detail. At small scales, this openness appears unavoidable. Gentle humour helps here as well. Nature, it seems, prefers to hedge its bets. It does not commit to a single outcome until asked, and even then, it follows a carefully weighted script rather than a rigid plan. The surprise is not that certainty disappears, but that so much order remains. By reframing wave-particle behaviour in statistical terms, probability brings coherence where confusion once lingered. Waves no longer need to be physical ripples. Particles no longer need predetermined paths. What exists between preparation and measurement is a set of possibilities, evolving smoothly, waiting to be expressed. This marks a decisive shift away from classical determinism. The future is no longer a single line extending forward, but a branching field of potential outcomes shaped by precise mathematical rules. Understanding this does not diminish reality. It deepens it. Probability in quantum mechanics is not a statement about ignorance. It is a statement about how nature works. Once this is accepted, the discomfort eases. What remains is a quieter, more flexible picture of the universe, one where certainty is not abandoned but redefined, emerging not from inevitability, but from consistency across countless individual events. Uncertainty is often misunderstood as a kind of failure, a lack of precision, a sign that something has gone wrong in the process of measurement. In everyday language, to be uncertain is to be unsure, to lack clarity or to miss important information. It is tempting, then, to interpret the uncertainty principle in the same way as a technical limitation that might be overcome with better instruments or more careful technique. That interpretation is comforting, and it is incorrect. In quantum mechanics, uncertainty is not a flaw in observation. It is a structural feature of how nature behaves at small scales. It does not arise because measuring devices disturb delicate systems, although disturbance can certainly occur. It arises because certain properties simply do not have exact values at the same time, no matter how they are probed. The most well-known example involves position and motion. In everyday experience, these feel inseparable. An object is somewhere, and it is moving in a particular way. With sufficient care, both can be measured precisely. Classical physics assumes this without hesitation. If the present state is known exactly, the future follows deterministically. Quantum mechanics places a quiet boundary here. The uncertainty principle states that the more precisely the position of a particle is defined, the less precisely its motion can be defined, and vice versa. This is not a statement about experimental clumsiness. It is a statement about the limits of definition itself. Nature does not allow both quantities to be sharply specified at once. This idea emerged in the mid-1920s through the work of Werner Heisenberg during the formative years of quantum mechanics. At the time, physicists were struggling to reconcile wave-like maths with particle-like observations. Heisenberg's insight was to focus not on visual models, but on what could be meaningfully described and predicted. What he found was striking. Attempts to sharpen certain predictions inevitably blurred others. The maths itself enforced this trade-off. No matter how the equations were arranged, the same constraint appeared. Precision in one domain demanded imprecision in the other. It is important to be clear about what this does and does not mean. The uncertainty principle does not say that particles wander aimlessly, or that anything can happen. The uncertainties involved are tightly constrained. They follow exact quantitative relationships that have been tested repeatedly. What is limited is not predictability in general, but simultaneous exactness. One helpful way to approach this is to think in terms of waves, not objects. A wave that is sharply localized in space must be composed of many different wavelengths. This mixture leads to uncertainty in how the wave evolves over time. A wave with a single, well-defined wavelength spreads out over space. The trade-off is built into the structure of waves themselves. Quantum systems behave in this wave-like manner at small scales. Position corresponds to how localized the wave is. Motion corresponds to how rapidly it changes. Trying to pin one down necessarily spreads the other. This is not a technological limitation, it is a mathematical and physical one. Common explanations sometimes describe uncertainty as arising because measurement disturbs the system. Shine light on a particle to see where it is, and the light knocks it around. While this can happen, it is not the core issue. Even in idealized situations where disturbance is accounted for, the uncertainty remains. The limitation persists even in principle. Another misconception is that uncertainty introduces randomness without structure. In fact, the opposite is true. The uncertainty principle is one of the reasons atoms are stable. If electrons could have both perfectly defined positions and perfectly defined motion, they would collapse into the nucleus. Uncertainty prevents this. It spreads the electron's presence in a way that allows atoms to exist at all. In this sense, uncertainty is protective. It imposes limits that make matter possible. Chemistry, materials, and life itself depend on it. The familiar world rests quietly on this rule, even though it contradicts classical intuition. There is also a tendency to interpret uncertainty as ignorance, as if particles secretly possess exact properties that are merely hidden. Decades of experimental work have challenged this view. Tests designed to reveal hidden deterministic variables have consistently failed to restore classical certainty. The probabilistic and uncertain structure appears to be fundamental, not provisional. This reinforces the shift introduced earlier. Probability is not a placeholder for missing information, it is a core feature of the theory. The uncertainty principle formalizes this by showing that even the questions that can be asked are constrained. Some pairs of properties cannot both be sharply defined, not because answers are missing, but because the questions themselves exceed what nature allows. It is worth pausing on how radical this is. Physics for centuries aimed to describe the world in terms of exact values evolving smoothly over time. The uncertainty principle redraws the boundaries of description. It says that the universe is not built from perfectly specified trajectories, but from ranges, distributions, and limits on simultaneous definition. This does not make the universe vague, it makes it precise in a different way. The uncertainties involved are not arbitrary. They are governed by exact relationships involving fundamental constants of nature. These constants set the scale at which quantum effects become noticeable. At human scale, the uncertainties are so small that classical certainty reemerges naturally. This is why everyday experience feels deterministic. even though it rests on probabilistic foundations. Gentle humour can help here. Nature, it seems, insists on a little personal space. It refuses to be pinned down too tightly, insisting that if one aspect is nailed down, another must be allowed to breathe. The rule is firm but not hostile. It simply defines how close description can get. Understanding this also resolves much of the confusion surrounding quantum measurement. Measurements do not reveal pre-existing exact values for all properties. They produce outcomes within allowed ranges. The uncertainty principle describes those ranges and the relationships between them. It is not a comment on human inadequacy, but on natural structure. Scientific bodies and laboratories around the world have verified these limits through countless experiments. From electron beams to ultra-cold atoms, the same patterns appear. Sharpen one quantity, and the complementary one spreads. The effect is not subtle, it is robust, repeatable, and unavoidable. By addressing these misunderstandings directly, the uncertainty principle becomes less threatening. It is not an attack on knowledge, it is a clarification of its scope. It tells where certainty is possible and where it is not, and it does so with mathematical and experimental precision. This formalizes the probabilistic view introduced earlier. Probability describes the range of possible outcomes. Uncertainty describes the limits on how narrowly those ranges can be defined. Together, they form a coherent framework, one that replaces classical determinism not with chaos, but with structured openness. There is a quiet elegance in how this fits together. The universe does not conceal its behavior out of spite. It follows rules that are consistent, testable, and deeply interconnected. Uncertainty is not an admission of defeat. It is a boundary that allows the rest of the structure to exist. Once this is accepted, tension fades. The desire for absolute precision relaxes. What remains is a deeper appreciation for how nature balances definition and freedom. The uncertainty principle does not undermine understanding. It refines it, setting the stage for everything that follows from the probabilistic fabric already in place. In this light, uncertainty is no longer a problem to be solved. It is a principle to be understood, and once understood, it reveals not a universe slipping out of control, but one that is quietly, consistently, and beautifully constrained. For much of scientific history, particles were treated as the basic units of reality, small, solid points moving through empty space. Even as quantum mechanics complicated this picture, it was still tempting to imagine electrons, photons, and other particles as tiny objects with fuzzy properties. The language of particles lingered because it felt familiar. It matched everyday experience, scaled down. Modern physics quietly lets go of that picture. At the deepest level currently understood, particles are not fundamental objects at all. They are events, ripples, localized excitations of something more basic that fills all of space. That underlying structure is known as a field, and quantum field theory is the framework that brings this idea together. A field, in this context, is not a material substance. It is a continuous entity that exists everywhere, even in regions that appear completely empty. Temperature is a familiar example at human scale. It exists throughout a room, rising and falling smoothly from place to place. A magnetic field behaves similarly, stretching invisibly through space, influencing objects without occupying them. Quantum fields extend this idea to its most fundamental form. According to quantum field theory, every type of particle is associated with its own field. There is an electron field, a photon field, and fields for every other known particle. These fields are not optional additions. They are always present, even when no particles are detected. What is normally called a particle is simply a localized disturbance in its corresponding field, much like a brief wave passing through an otherwise calm surface. This shift in perspective is profound. It replaces object-based thinking with process-based understanding. Instead of asking where a particle is, it becomes more accurate to ask how a field is behaving in a particular region. Instead of imagining objects moving through emptiness, reality becomes a tapestry of overlapping fields, continuously interacting and occasionally producing detectable excitations. This framework grew out of the need to combine quantum mechanics with special relativity. Early quantum theory worked well for isolated systems, but it struggled to handle situations where particles could be created or destroyed, such as high-energy collisions. Experiments showed that particles could appear and disappear, converting energy into matter and back again. A theory built around permanent objects could not accommodate this behavior cleanly. Quantum field theory solved this by treating creation and destruction as natural features. Fields can be excited or calm. Energy added to a field produces particles. Energy removed allows them to vanish. Nothing fundamental is lost or gained. The field remains. This view underlies the standard model of particle physics, the most successful description of fundamental interactions currently available. The standard model organizes known particles and forces into a coherent framework built entirely from interacting quantum fields. Electromagnetism, the weak nuclear interaction, and the strong nuclear interaction all arise from field interactions governed by precise rules. The predictive power of this model is extraordinary. Calculations based on quantum field theory match experimental results to astonishing accuracy. Certain quantities have been confirmed to more than 10 decimal places. This level of agreement is not accidental. It reflects a framework that captures something deeply real about how nature operates. Experimental confirmation of this picture comes from some of the most ambitious scientific efforts ever undertaken. Facilities such as the Large Particle Accelerators, operated by international collaborations, provide direct evidence for field-based behavior. At CERN, particles are accelerated to enormous energies and collided, briefly disturbing the underlying fields enough to reveal new excitations. The results consistently support the field picture. New particles appear exactly where and when the theory predicts. What is especially striking is that even empty space participates in this behavior. A region with no particles present is not inert. Fields are still there, fluctuating gently, constrained by quantum rules. These fluctuations can have measurable effects, confirming that fields are not abstract mathematical conveniences, but physically active components of reality. This understanding deepens earlier ideas about uncertainty and probability. If particles are excitations of fields, then uncertainty is no longer just about missing information. It reflects the fact that fields themselves have intrinsic variability. Probabilities describe how excitations emerge from continuous structures, not how objects hide their properties. It also reframes earlier confusion about wave and particle behavior. Waves are not optional descriptions layered onto particles. They're expressions of how fields evolve. The spread of a probability distribution reflects the underlying field dynamics. When a particle is detected, it is not because a tiny object finally chose a location. It is because a field interaction produced a localized event. There is something quietly elegant about this. The universe is no longer a collection of things bouncing around in emptiness. It is a set of processes unfolding within ever-present structures. Fields interact, exchange energy, and produce the appearances we label as particles. Objects become moments. Stability becomes pattern. Gentle humour fits here as well. The idea of particles turns out to be a useful illusion, like waves on the surface of the ocean being mistaken for separate entities. The waves feel real, behave consistently, and can be measured precisely. Yet the deeper reality is the water itself. In quantum field theory, particles are the waves, fields are the ocean. This perspective also explains why the same particle can be created in different places under different conditions, yet always behave identically. It is not because countless identical objects exist independently. It is because each excitation arises from the same underlying field, governed by the same rules everywhere. Scientific institutions across the world continue to test this framework, pushing it into new regimes of energy and precision. So far, it has held up remarkably well. Where it succeeds, it does so decisively. Where it falters, it points clearly to the questions that remain open, particularly where gravity enters the picture. By replacing object-based thinking with field-based understanding, quantum field theory brings coherence to many of the strange features encountered earlier. Uncertainty, probability, and dual behavior all find a natural home within this deeper structure. The universe does not consist of tiny beads stitched together by force. It consists of fields, continuously present, occasionally excited, and endlessly interacting. Once this shift is made, earlier discomfort begins to fade. The strange behavior of particles no longer feels like a series of exceptions. It becomes the expected behavior of a world built from fields rather than objects. And in that world, solidity, certainty, and individuality emerge not as fundamentals, but as patterns arising from a far richer and more subtle foundation. Separation feels fundamental. Two objects occupy different places. They move independently. What happens to one does not instantly affect the other. This assumption is woven deeply into everyday reasoning, reinforced by distance, time, and the apparent isolation of things in space. Even earlier ideas about fields, continuous and overlapping as they are, still allow for local behavior, where interactions diminish with distance. Quantum mechanics quietly unsettles this picture. There are situations where two particles cannot be described independently at all, even when separated by vast distances. Their properties become linked, not because of ongoing interaction, but because they share a single quantum description. This phenomenon is known as entanglement, and it represents one of the most striking departures from classical thinking. Entanglement does not mean that particles communicate secretly or exchange signals faster than light. It means something subtler. The system must be treated as a whole. The state of one particle cannot be fully specified without reference to the other. What appears to be two objects behaving separately is, at a deeper level, one system expressing itself in two locations. This shared behavior arises naturally from the quantum framework already in place. When particles are created together or interact in specific ways, their properties become correlated. Measuring one reveals information about the other, not because information has travelled between them, but because the information was never separate to begin with. Consider a pair of particles produced in a single process, their properties linked by conservation laws. Before measurement, neither particle has a definite value for certain properties. Instead, the system as a whole has a well-defined structure. When one particle is measured, the system responds by producing a consistent outcome for the other, no matter how far apart they are. This is where intuition begins to struggle. Distance usually weakens influence. Here, it does not. The correlations persist even when particles are separated by kilometers or more. Experiments have confirmed this repeatedly, using photons sent through optical fibers and free space, measured by detectors operating independently and far apart. The key word is correlation. Outcomes are linked in ways that cannot be explained by shared history alone. Classical explanations suggest that particles might carry hidden instructions, predetermined responses that are merely revealed upon measurement. If that were the case, the the correlations would obey certain statistical limits. They do not. In the 1960s, physicist John Bell derived a set of inequalities that any theory based on local hidden variables must satisfy. These inequalities provided a clear experimental test. If measurements violated the inequalities, then no local explanation based on pre-assigned properties could account for the results. Experiments were carried out, again and again, with increasing sophistication and tighter controls. The inequalities were violated. The results were unambiguous. Nature does not behave as if entangled particles carry independent instructions waiting to be uncovered. The correlations are stronger than any classical local theory allows. This does not mean that information travels instantaneously. It means that the underlying description is not built from independent parts. This is a crucial distinction. Entanglement does not allow faster-than-light communication. While measuring one particle affects the description of the system, it does not allow control over the outcome. Each individual result appears random. Only when results are compared later do the correlations become visible. No usable signal can be sent in this way. This preserves consistency with relativity. Cause and effect remain bounded by the speed of light. What changes is not the flow of information, but the structure of description. The universe, at small scales, does not insist on separability as a fundamental principle. Seen through the lens of quantum fields, this becomes more intuitive. Fields extend throughout space. Excitations within them need not be independent if they arise from a shared process. Entanglement reflects the continuity of the underlying fields rather than the independence of the excitations. What appears as non-local behavior emerges naturally from a framework that was never fully local to begin with. This challenges the idea of objects as self-contained units. In the classical picture, objects possess properties internally, regardless of context. Quantum mechanics replaces this with a relational view. Properties are defined through interactions and shared states. Independence becomes an approximation, valid at large scales, but incomplete at small ones. There is a quiet elegance in this shift. It suggests that the universe is more interconnected than appearances suggest, without being chaotic or uncontrolled. Entanglement does not collapse space or erase distance. It reveals that some features of reality are distributed across systems rather than residing in isolated pieces. Gentle humour helps soften the surprise. Entangled particles behave less like distant strangers and more like dance partners who learned the routine together and continue in sync long after the music has faded. No signals are exchanged. They simply remain coordinated because they were never separate in the first place. Experimental confirmation of entanglement has become routine in modern physics laboratories. Photons are entangled and sent in opposite directions. Measurements are made independently. Results align exactly with quantum predictions and consistently violate classical limits. These experiments are not rare demonstrations. They are standard tools used to test and refine understanding. The reliability of these results is what makes entanglement so important. It is not an exotic curiosity. It is a predictable feature of quantum systems. Technologies such as quantum cryptography rely directly on entanglement, using its correlations to detect interference and ensure security. The behavior is strange, but it is also dependable. This further reinforces the move away from object-based thinking. If particles were truly independent objects, entanglement would be impossible. The fact that it exists, and exists reliably, suggests that independence is not fundamental. It is emergent, arising when interactions fade and correlations become negligible. At human scales, this emergence is complete. Objects behave independently. Causes remain local. The classical world reasserts itself. At quantum scales, however, the seams remain visible. Systems retain memory of shared origins. Fields carry correlations across space without effort. Understanding entanglement requires patience, not reinterpretation of causality. Nothing travels faster than light. Nothing breaks the structure of space-time. What changes is the assumption that reality can always be divided cleanly into separate parts. This builds directly on earlier ideas about fields and probability. Probabilities apply not just to individual particles, but to entire systems. The wave description encompasses all entangled components at once. Measurement selects outcomes from this shared structure, producing results that appear local but reflect non-local organization. Once this is accepted, entanglement becomes less mysterious. It is no longer a paradox to be resolved, but a feature to be understood. The universe does not insist that everything be separable. It allows relationships to persist across distance, not through communication, but through shared description. In this way, entanglement quietly reshapes how reality is imagined. Objects are no longer the final units. Systems take precedence. Connections matter as much as components. And beneath the apparent independence of things lies a deeper coherence, patiently expressed through correlations that refuse to fade, no matter how far apart their expressions may appear. Measurement sounds passive. Something is observed. A reading is taken. A value is recorded. In everyday life, measuring feels like a gentle act, a way of revealing what was already there. A ruler does not change the length of a table. A clock does not alter the passage of time. Observation appears separate from the thing being observed. Quantum mechanics quietly removes that separation. At small scales, measurement is not a neutral glance. It is a physical interaction. Energy is exchanged. Systems become linked. Outcomes are produced through contact, not revealed by inspection. Nothing mystical is required, and no special role is reserved for human awareness. What matters is not who looks, but what interacts. This distinction is essential, because misunderstanding it has led to decades of unnecessary confusion. Popular accounts sometimes suggest that consciousness causes reality to crystallize, or that particles behave differently when watched. These ideas are compelling, but they are not supported by how quantum experiments actually work. Detectors do not need eyes. Screens do not need awareness. Atoms register outcomes just as effectively as people do. In quantum experiments, a measurement occurs when a system interacts with something large enough to leave a stable record. A photon strikes a detector. An electron triggers a signal. An atom emits light that is absorbed elsewhere. These interactions are physical processes governed by the same rules as everything else. No thought is required. The difficulty lies not in the act of measurement itself, but in how it fits into the broader description of quantum systems. Before measurement, systems are described by probabilities. After measurement, a specific outcome appears. The transition between these descriptions is what physicists call the measurement problem. It is important to note what this problem is not. It is not a question about human perception. It is not about when someone becomes aware of a result. It is about how a probabilistic description gives rise to a single event. Early architects of quantum theory were acutely aware of this tension. Niels Bohr, one of the central figures in its development, emphasized that quantum systems cannot be separated from the conditions under which they are measured. According to what became known as the Copenhagen interpretation, physical properties are not attributes carried independently by particles. They are defined through interaction. This does not mean that reality depends on observers. It means that descriptions depend on context. The arrangement of an experiment determines what can meaningfully be said about a system. Change the interaction, and different properties become relevant. Bohr argued that it is a mistake to imagine quantum objects possessing a complete set of definite properties at all times. Some properties only become well defined when measured. Others remain undefined, not because they are hidden, but because the situation does not allow them to exist simultaneously. This view aligns naturally with everything encountered so far. Probability replaces certainty. Uncertainty limits simultaneous definition. Fields underlie particles. Entanglement links systems across distance. Measurement fits into this picture not as an intrusion, but as participation. When a quantum system is measured, it becomes entangled with the measuring device. The system and apparatus form a combined whole. From the perspective of the apparatus, a definite outcome appears. From the perspective of the larger quantum description, the interaction has produced a stable correlation. This is why disturbance is not the right word. Measurement does not simply knock a system out of its natural state. It creates a new state that includes both system and measuring device. The outcome is not uncovered. It is produced through interaction. A helpful everyday analogy is conversation. Words do not exist as fixed objects waiting to be discovered. They arise through interaction between speakers. Once spoken, they become part of the shared environment. Measurement is similar. It is an event that brings something into being within a particular context. This perspective also dissolves much of the confusion surrounding collapse. The idea that a wave function suddenly collapses can sound dramatic, even violent. In practice, it describes the transition from a probabilistic description to a definite record. Once an outcome is recorded in a stable way, probabilities are no longer needed to describe that particular event. Nothing special happens at the moment of human awareness. The outcome exists as soon as it is registered physically. Consciousness enters later, reading a result that has already taken place. This understanding is supported by countless experiments. Automated detectors register quantum events without supervision. Data is stored, analyzed later, and compared across laboratories. The results do not wait for observation. They are produced by interaction and preserved by physical systems. The measurement problem remains an active area of research, not because measurement is mysterious, but because the boundary between quantum and classical descriptions is subtle. Large systems behave classically not because quantum rules stop applying, but because interactions spread information so widely that probabilistic descriptions become effectively irreversible. Once information about an outcome is dispersed into many degrees of freedom, the system behaves as if a single result has been selected permanently. This is why measuring devices appear classical. They are designed to amplify tiny events into robust records. Understanding measurement in this way also clarifies its relationship to entanglement. Measurement is a special case of entanglement, where one part of the system is large, stable, and capable of recording outcomes. The correlations produced become one-sided, favouring definite records over reversible evolution. Gentle humour fits here too. The universe does not wait to be noticed. It does not pause politely until someone looks. Measurements happen because things bump into other things, exchange energy, and leave traces behind. Awareness arrives afterward, like reading yesterday's news. Stabilizing the concept of measurement removes a great deal of unnecessary tension from quantum mechanics. There is no need to invoke consciousness as a causal agent. There is no need to imagine reality flickering in and out of existence. There is only interaction, governed by precise rules, producing outcomes that become part of the physical world. This view also restores continuity with the rest of physics. Measurement is not a special category reserved for quantum systems. All measurement, at every scale, involves interaction. The difference is that at small scales, interaction cannot be ignored or treated as negligible. Seen this way, measurement is not an obstacle to understanding quantum reality. It is one of its most revealing features. It shows how possibilities become events, how probabilities give way to records, and how the abstract structure of the theory connects to the concrete world. By emphasizing participation rather than disturbance, measurement becomes less threatening and more coherent. It is not an act of interference that breaks a delicate system. It is the natural way systems relate to one another. Once this is appreciated, the lingering mystery softens. Measurement is no longer the point where physics gives up. It is the point where interaction becomes visible, and in that visibility, the quiet logic of quantum mechanics continues to hold, consistent, testable, and firmly grounded in the physical world. Quantum mechanics has an unusual reputation. It is one of the most successful theories ever developed, yet it is also one of the most debated. Not because its predictions fail, but because its meaning remains open to interpretation. This combination can feel unsettling. In most areas of science, disagreement signals uncertainty or incomplete understanding. Here, disagreement persists even while the maths works flawlessly. The reason is subtle. Quantum mechanics is extraordinarily clear about what will be observed. It is far less explicit about what is happening in between. The equations of quantum theory describe how probabilities evolve over time. They specify how systems behave when they interact and what outcomes will be produced. These rules have been tested for over a century and confirmed with remarkable precision. Wherever experiments have been performed carefully, the results align with the same mathematical framework. And yet, that framework allows more than one way of telling the story. This is why multiple interpretations exist. The maths does not dictate a single narrative about what reality is doing when it is not being measured. It tells how to calculate results, not how to imagine the underlying process. Different interpretations step into that gap, offering distinct ways of thinking about the same formal structure. One of the earliest and most influential approaches is commonly known as the Copenhagen interpretation. Associated with figures such as Niels Bohr, it emphasizes the role of measurement and context. In this view, quantum systems do not possess definite properties independent of interaction. Physical quantities become meaningful only when measured, and the theory concerns what can be said about outcomes, not what exists unobserved. Copenhagen thinking is often pragmatic. It does not attempt to describe an underlying mechanism behind the equations. Instead, it treats the mathematical framework as complete in itself. Questions about what happens between measurements are considered either undefined or unnecessary. This approach has the advantage of restraint. It avoids adding assumptions beyond what experiments require. For some, however, this restraint feels unsatisfying. The desire to describe an objective reality unfolding continuously has a long history in physics. This motivation gave rise to alternative interpretations that retain the same maths while telling a different story. One such approach is the many worlds interpretation, proposed by Hugh Everett in the 1950s. Instead of treating measurement as a special event where probabilities collapse into a single outcome, this view suggests that all possible outcomes occur. Each outcome corresponds to a different branch of the universe, all evolving according to the same underlying equations. In this picture, probability reflects the relative weight of these branches rather than the chance of a single outcome. There is no collapse. The wave description continues smoothly and universally. Measurement becomes a process of branching rather than selection. This idea can sound extravagant, even overwhelming. Yet it does not introduce new maths. It takes the existing equations at face value and applies them universally, including to measuring devices and observers. Its boldness lies in interpretation, not prediction. At the other end of the conceptual spectrum lies pilot wave theory, associated with David Bohm. This approach reintroduces determinism by proposing that particles have definite positions at all times, guided by an underlying wave. The wave evolves according to standard quantum equations, while particles follow precise trajectories influenced by it. In this view, probability arises from ignorance about initial conditions rather than fundamental indeterminacy. The wave provides the structure, the particle provides the outcome. Both coexist, linked by clear rules. Pilot wave theory restores a sense of continuous motion and objective reality. However, it does so at a cost. It requires non-local influences, where changes in one part of the system can affect distant parts instantaneously. While this does not allow faster-than-light communication, it challenges intuitive notions of locality. What is remarkable is that all of these interpretations agree on what experiments will show. Whether one prefers Copenhagen restraint, Everett branching, or Bohmian guidance, the calculated probabilities are identical. No experiment currently distinguishes between them. This is not a weakness of quantum mechanics, it is a reflection of its completeness. The theory provides all the information needed to predict outcomes. The interpretations differ only in how that information is framed conceptually. This distinction between physics and philosophy is essential. Physics concerns testable predictions. Philosophy concerns meaning, explanation, and intuition. Interpretations belong primarily to the second category. They influence how the theory is understood, taught, and imagined, but they do not alter its empirical success. This is why debates about interpretation can persist indefinitely, without being resolved by experiment. They are not disagreements about facts, they are disagreements about how to narrate those facts. There is a temptation to treat one interpretation as more correct than the others. Often, this preference reflects personal taste. Some find comfort in minimalism, others prefer realism, some are drawn to determinism, others accept indeterminacy as fundamental. The maths remains indifferent to these preferences. Gentle humour helps here. Quantum mechanics is like a perfectly accurate recipe that refuses to explain why the dish tastes the way it does. Different cooks invent different stories about the flavour, but the meal comes out the same every time. Understanding this can be liberating. It removes the pressure to choose the right interpretation. One can work effectively with the theory without committing to a particular metaphysical stance. Many practicing physicists do exactly that, using the maths daily while remaining agnostic about its deeper meaning. This also reframes earlier debates about measurement. Whether one views measurement as collapse, branching, or guidance, the observable results are the same. The differences lie in how one imagines the unseen processes connecting preparation to outcome. By separating physics from philosophical framing, much of the tension surrounding quantum mechanics dissolves. The theory does not demand belief in any particular story. It demands only that its rules be followed when making predictions. This separation also reflects scientific humility. Quantum mechanics tells what can be known and calculated with extraordinary precision. It remains silent on certain questions not because it is incomplete, but because those questions may not have operational meaning within the theory. Seen this way, multiple interpretations are not a sign of confusion. They are a sign of flexibility. The same mathematical structure supports different ways of thinking, each consistent with observation. The universe, it seems, is content to be calculated correctly, without insisting on a single explanation. The equations do their work quietly and reliably. The stories built around them remain optional. And in that quiet separation between calculation and interpretation, quantum mechanics reveals something subtle. Understanding does not always require agreement on meaning. Sometimes, it requires only that predictions be precise, experiments be honest, and expectations remain open to more than one way of seeing the same underlying structure. Time feels dependable. It moves forward steadily, one moment following the next, carrying events along in a clear sequence. Clocks tick, days pass, causes precede effects. This steady flow is so deeply embedded in experience that it is rarely questioned. Even earlier disruptions to intuition left time mostly untouched. Space could blur. Objects could spread into probabilities. Yet time seemed to remain a reliable backdrop against which everything else unfolded. Quantum physics begins to soften even that certainty. In quantum descriptions, time behaves differently from almost every other quantity. Position becomes uncertain, motion spreads into ranges, energy arrives in discrete amounts. But time, oddly, is not treated as something that can fluctuate or become probabilistic in the same way. Instead, it enters the theory as an external parameter, a silent coordinator rather than an observable feature. This asymmetry is not a philosophical choice, it is built into the structure of the theory. In quantum mechanics, position, momentum, and energy are all quantities that can be measured, exchanged, and placed into uncertain relationships with one another. Time is different. It is not represented as something the system possesses. It is something the system evolves within. This distinction can feel subtle, but its consequences are significant. There is no time operator in standard quantum mechanics in the same sense that there are operators for position or energy. This means that time cannot be treated symmetrically with other quantities. It cannot be measured in the same way. It does not participate directly in uncertainty relations. At first glance, this might seem like a technical detail. In practice, it reveals a deeper tension. Quantum mechanics describes how systems change with time, but it does not explain what time itself is. It assumes a background flow against which probabilities evolve. This assumption works extremely well for laboratory experiments, where clocks are external, stable, and classical. But it becomes increasingly strained when quantum systems interact with gravity, where time itself is dynamic. Relativity reshaped the understanding of time long before quantum theory matured. According to relativity, time is not absolute. It depends on motion and gravitational influence. Clocks tick at different rates depending on speed and position in a gravitational field. Space and time form a unified structure, flexible and responsive to energy and mass. Quantum mechanics, by contrast, treats time as fixed. It flows uniformly and universally, unaffected by the system under study. This difference creates a conceptual mismatch. Each theory works exceptionally well within its domain. Together, they refuse to blend smoothly. This tension becomes unavoidable when attempting to describe situations where quantum effects and gravity are both important. Near black holes, in the early universe, at extremely small scales where spacetime itself may fluctuate. In these regimes, the assumption of a fixed background time becomes questionable. This is where the idea of temporal uncertainty begins to appear, not as a formal rule like spatial uncertainty, but as a consequence of incomplete description. If spacetime is subject to quantum effects, then time itself may not be perfectly defined. The familiar flow could emerge only approximately, much as classical certainty emerges from quantum probability at large scales. Researchers exploring quantum gravity grapple with this problem directly. Different approaches suggest different possibilities. Some propose that time emerges from deeper, timeless structures. Others suggest that time remains meaningful only when systems interact in specific ways. What they share is a recognition that time may not be fundamental in the way it feels. This can sound unsettling, but it does not undermine everyday experience. Just as solidity remains dependable despite atomic emptiness, time remains reliable despite deeper ambiguity. The uncertainty arises not in daily life, but in extreme regimes far removed from ordinary conditions. There is also a quiet logic to treating time differently. Time orders events. It provides sequence and causality. Allowing it to fluctuate freely could dissolve the structure needed for consistent description. Quantum mechanics preserves order by keeping time external, even while allowing other quantities to blur. Yet this preservation comes at a cost. It leaves unanswered questions about the nature of time itself. Is time something that exists independently, or is it a measure of change? Does it flow, or is flow an emergent sensation arising from increasing complexity and entropy? These questions are not new, but quantum mechanics gives them sharper edges. When systems are described probabilistically, and when outcomes depend on interaction, the meaning of before and after becomes more delicate. In entangled systems, correlations do not fit neatly into simple temporal order. Measurement outcomes appear linked in ways that do not respect naive notions of sequence. Still, causality remains intact. No influence travels backward in time, no signal outruns light. The uncertainty here is not about causation, but about description. It is about how time is represented within the theory, not about whether time behaves sensibly. Gentle humour helps soften this. Time, it seems, is treated like a trusted assistant. Always present, always reliable, but never asked to explain itself. Quantum mechanics is happy to use time without questioning its credentials. This pragmatic approach has served physics well. Experiments proceed, predictions match observation. Technologies relying on precise timing, such as atomic clocks and navigation systems, function with astonishing accuracy. These systems even incorporate relativistic corrections, blending classical and relativistic times seamlessly in practice. Yet beneath this success, the conceptual tension remains. Quantum mechanics and relativity tell different stories about time. One treats it as fixed and external. The other treats it as dynamic and intertwined with space. Reconciling these views remains one of the deepest challenges in theoretical physics. Introducing temporal uncertainty calmly allows this challenge to be acknowledged without alarm. The universe does not break down when time becomes unclear at small scales. It continues to behave consistently within each framework. The uncertainty lies in how these frameworks fit together, not in their individual reliability. This extends the idea of uncertainty beyond space. Not only are positions and motions limited in simultaneous definition, but the role of time itself resists complete clarity. The boundaries of description shift again, reminding us that intuition has limits not just in where things are, but in when things happen. Seen this way, time remains what it has always been in experience. It carries events forward, orders memories, and anchors causality. Quantum mechanics does not deny this. It simply suggests that beneath that steady flow lies a deeper structure, one that has yet to be fully understood. The uncertainty here is not a flaw to be corrected. It is a signpost marking the edge of current understanding. Beyond it lies a theory still taking shape, one that will need to explain not only how things change in time, but what time itself truly is. Space feels like the quietest thing imaginable. It stretches calmly between objects, offering room to move, room to exist, room to separate one thing from another. In everyday experience, space behaves like a stage. Events happen within it, but it does not appear to participate. It does not react. It does not change simply because something passes through. For a long time, physics shared this intuition. Classical descriptions treated space as a passive backdrop, a fixed arena in which matter and energy played out their interactions. Even when space and time were woven together through relativity, space-time still behaved smoothly, bending in response to mass and energy, but remaining continuous and well-defined at every point. Quantum theory quietly raises the possibility that this picture, too, may be incomplete. If matter and energy are governed by quantum rules, and if gravity responds to energy and mass, then it becomes natural to ask whether space itself might also possess a quantum structure. Not merely a smooth container, but something with its own microscopic behaviour, hidden beneath the calm surface perceived at large scales. This idea does not arise from speculation alone, it emerges from the tension already encountered. Quantum mechanics treats time differently from space. Relativity binds them tightly together. If time resists clean integration into quantum theory, then space likely does as well. The two are not easily separated. One possibility explored by physicists is that spacetime is not infinitely smooth. At extremely small scales, far beyond direct measurement, it may have a discrete or granular structure. Not chunks in the everyday sense, but fundamental units of geometry, arranged in patterns that give rise to smooth space only when viewed from far enough away. This is a delicate idea and must be handled carefully. There is no experimental confirmation yet, but it is motivated by the same logic that led to quantization elsewhere. Smooth assumptions fail at small scales. Discreteness emerges where continuity once seemed obvious. Spacetime fluctuations are one way to imagine this. At very small scales, geometry itself may fluctuate, changing subtly from moment to moment. Distances could vary slightly. Angles could blur. These variations would be utterly negligible at human scale, completely invisible to ordinary measurement, yet significant when probing the deeper structure of reality. The term spacetime foam is sometimes used to evoke this idea, though the imagery can mislead. Nothing is bubbling or churning in a dramatic sense. The fluctuations are not chaotic. They are constrained by rules, just as quantum uncertainty constrains particles and fields. The image is meant only to suggest that space is not perfectly rigid when examined closely enough. One approach that explores this possibility is known as loop quantum gravity. In broad terms, it attempts to describe space as composed of tiny quantized loops or networks, woven together to form geometry itself. Distances and areas arise from the relationships between these loops, rather than existing independently. The appeal of this approach lies in how it treats space as an active participant rather than a passive container. Geometry becomes something that can evolve, interact and respond, much like other physical systems. Space is no longer just where things happen, it is part of what happens. It is important to emphasize caution here. Loop quantum gravity is one of several competing approaches, and none has yet been confirmed experimentally. The details remain under development. What matters for now is the shift in perspective it represents. Space is no longer assumed to be smooth and continuous by default. That assumption is being questioned. This questioning mirrors earlier developments. Matter turned out not to be solid. Energy turned out not to be continuous. Light refused a single identity. Probability replaced certainty. Time lost its simplicity. In each case, the breakdown of intuition led not to disorder, but to deeper structure. Space may be following the same path. If space has quantum properties, then distance itself may be subject to fundamental limits of definition. Just as position and motion cannot both be perfectly specified, geometry may resist infinite precision. This would not mean that rulers become unreliable or that buildings wobble unpredictably. It would mean that at scales far beyond practical concern, the concept of distance reaches a natural boundary. This complements the earlier discussion of time. If time becomes unclear at quantum scales, it would be surprising if space remained untouched. Together, they form spacetime, and it is reasonable to expect that both share in whatever deeper structure lies beneath classical description. There is also a conceptual elegance in this idea. It avoids treating space as something separate from the rest of physics. Instead, space becomes part of the same story, governed by rules, subject to limits, capable of change. This unifies geometry with matter and energy rather than isolating it. Gentle humour can be found in how stubborn the backdrop turns out to be. Space, once imagined as the ultimate passive observer, may have been quietly participating all along, not loudly, not dramatically, but with the same disciplined subtlety seen elsewhere in quantum physics. Avoiding speculative certainty is essential here. These ideas are not settled facts. They are informed attempts to reconcile theories that work extraordinarily well in their own domains but resist combination. The universe has not yet revealed whether space truly comes in quantum units, or whether a different resolution awaits discovery. What can be said with confidence is that treating space as purely passive no longer feels adequate. The success of quantum field theory, the persistence of uncertainty, and the tension with relativity all point toward a more active role for geometry. Scientific institutions around the world continue to explore these questions, using mathematical insight, theoretical consistency, and indirect experimental clues. The work is careful and incremental. There are no shortcuts here, and no dramatic declarations. For now, the most important shift is conceptual. Space is no longer taken for granted. It is no longer assumed to be an empty stage. It is considered a candidate for deeper structure, one that may share in the same quantum principles governing everything else. This challenges a deeply ingrained habit of thought. It invites a quieter, more flexible view of reality, one where even the emptiest regions of the universe are not truly inert, but structured in ways that only reveal themselves when intuition steps aside. Seen alongside the uncertainty surrounding time, this idea forms a coherent extension rather than a rupture. Space and time together become part of the question, not the unquestioned foundation. And in that shift, the universe once again reveals itself not as less understandable, but as more subtle than it first appears. Nothing feels simple. It suggests absence, emptiness, a quiet lack of activity. In everyday language, a vacuum is a place where nothing happens and nothing exists. Remove all matter, drain away air, extinguish light, and what remains seems like pure stillness. An empty container. A blank background. Quantum physics gently disagrees. In quantum theory, a vacuum is not an inert void. It is the lowest energy state of a system, not a state of non-existence. Even when no particles are present, the underlying fields remain. They cannot be switched off. They persist throughout space, following their rules, even when nothing obvious is happening. This distinction matters. It transforms the idea of emptiness from absence into structure. A quantum vacuum is quiet, but it is not dead. It is active in subtle, disciplined ways. According to quantum field theory, every field fills all of space at all times. When a field is in its lowest energy configuration, it produces no particles that can be directly detected, yet the field still exists. And because of quantum uncertainty, it cannot be perfectly still. Its energy cannot be pinned to an exact value with absolute precision. As a result, fields in the vacuum undergo tiny fluctuations. These fluctuations are not random chaos. They are constrained by strict rules. Energy briefly concentrates, then disperses. Excitations appear and vanish too quickly to be directly observed. These fleeting effects are often described using the language of virtual particles. The term virtual particle can be misleading if taken too literally. These are not particles popping in and out of existence like miniature fireflies. They are temporary disturbances in a field, mathematical expressions of interaction rather than independent objects. They do not violate conservation laws, they do not persist. They reflect the fact that fields cannot remain perfectly still. One way to think about this is to return to uncertainty. If energy and time cannot both be defined with perfect precision, then brief deviations in energy are allowed, provided they are quickly balanced. The vacuum accommodates these fluctuations without becoming unstable. It remains the lowest energy state overall, even while local activity briefly appears. This behavior might seem abstract, but it has measurable consequences. One of the most striking pieces of evidence for vacuum activity is known as the Casimir effect. When two uncharged metal plates are placed extremely close together in a vacuum, they experience a tiny attractive force. Nothing appears to be pulling them together. There is no electric charge involved. Yet the force is real and measurable. The explanation lies in how vacuum fluctuations behave near boundaries. Between the plates, only certain field fluctuations are allowed. Outside the plates, more fluctuations are possible. This imbalance creates a pressure difference, gently pushing the plates together. The effect is subtle, but it has been confirmed experimentally many times with increasing precision. The Casimir effect is important not because of its practical impact, but because of what it demonstrates. The vacuum is not empty in the classical sense. Its structure can be altered. Its behavior can produce forces. Emptiness follows rules. This reinforces a recurring theme. Quantum physics does not replace order with chaos. It replaces intuitive simplicity with disciplined complexity. The vacuum behaves predictably, even if its behavior defies everyday expectations. Redefining nothing in this way has broad implications. It means that removing particles does not remove physics. Fields remain. Fluctuations persist. Interactions continue quietly in the background. Space, already understood as potentially active, now hosts a vacuum that participates rather than vanishes. There is also a comforting consistency here. The same uncertainty that prevents particles from having exact properties also prevents emptiness from being perfectly empty. The same framework governs matter, energy, space, and absence alike. Nothing gets special exemptions. Gentle humour helps soften the surprise. The universe, it seems, refuses to do absolutely nothing, even when asked politely. Even when everything visible is removed, it remains subtly busy, following rules with quiet determination. It is important to avoid exaggeration. Vacuum fluctuations do not mean that energy can be extracted freely from empty space, or that the universe is bubbling wildly beneath the surface. The effects are tiny, tightly constrained, and carefully balanced. The vacuum is stable. It does not collapse or explode. Its activity is gentle and controlled. Scientific institutions around the world have studied these effects in laboratories designed to isolate and measure extremely small forces. Advances in precision measurement have made it possible to observe vacuum behavior directly, not as speculation, but as experiment. The results consistently support the same picture. The vacuum has structure. That structure matters. This understanding also connects naturally to earlier ideas about fields and space. If fields fill space, and if space itself may have quantum properties, then the vacuum becomes a meeting point. It is where field behavior, spatial structure, and uncertainty intersect. Emptiness is no longer an afterthought. It is an active participant in the story. This reframing challenges one of the deepest intuitions inherited from classical thinking, that something and nothing are sharply distinct. Quantum physics replaces that sharp boundary with a gradient. There are fewer particles, fewer excitations, less energy. But there is never absolute absence. That does not diminish the meaning of nothing, it enriches it. Nothing becomes a state with character rather than a lack of substance, a condition defined by rules rather than by emptiness. The purpose of this shift is not to mystify, but to clarify. When physicists speak about the vacuum, they are not invoking mystery. They are describing a well-defined physical state with measurable properties. The language may sound surprising because everyday intuition lacks the tools to describe it comfortably. Seen in this light, the vacuum fits neatly into the broader picture already unfolding. Matter is mostly empty yet structured. Energy is discrete yet dependable. Light refuses simple identity. Probability governs outcomes. Space may be active. Time becomes subtle. Emptiness, too, turns out to be governed rather than absent. This builds directly on the idea of quantum space. If space is not passive, then the vacuum within it cannot be passive either. Both participate. Both fluctuate within limits. Both contribute to how reality behaves at its most fundamental level. There is a quiet reassurance in this. The universe does not fall apart when things are removed. It does not rely on objects alone to exist meaningfully. Its structure persists even in apparent absence, following rules that remain stable, testable, and precise. Redefining nothing does not make reality less solid. It makes it more coherent. Emptiness is no longer a gap in understanding. It is part of the same disciplined framework that governs everything else. And once that is accepted, the idea of a truly empty void fades gently away, replaced by a quieter, richer picture. One where even the absence of things is shaped by law, and where nothing, far from being nothing at all, plays its part with remarkable consistency. Instability is often treated as something to be feared. In everyday life, stability comes from firmness, precision, and control. A structure stands because its parts are fixed in place. A system behaves predictably because its components follow clear paths. From this perspective, uncertainty sounds like a recipe for collapse rather than coherence. At the atomic scale, the opposite is true. Atoms are stable precisely because uncertainty exists. Without it, matter as it is known would not survive for even a fraction of a second. The very thing that feels unsettling in theory turns out to be the quiet reason the physical world holds together. Early attempts to picture atoms using classical ideas ran into immediate trouble. If electrons were treated as tiny charged objects orbiting a nucleus, much like planets around a star, they should continuously lose energy. Accelerating charges emit radiation. Losing energy would cause electrons to spiral inward, collapsing into the nucleus. According to classical physics, atoms should be catastrophically unstable. They are not. Every atom in the universe, from the hydrogen in distant stars to the carbon in living cells, remains stubbornly intact. This stability demanded an explanation that classical reasoning could not provide. Quantum mechanics offered one, and it rests squarely on uncertainty. Because an electron cannot have both a perfectly defined position and a perfectly defined motion, it cannot be confined to an arbitrarily small region without consequence. Squeezing an electron too tightly in space forces its motion to become highly uncertain. That uncertainty in motion corresponds to high energy. The system resists collapse not through rigidity, but through balance. The electron does not orbit the nucleus along a precise path. Instead, it occupies a region described by probabilities. These regions are not vague or arbitrary. They have well-defined shapes and energies, determined by the quantum rules governing the system. The lowest energy configuration spreads the electron out just enough to minimize the total energy. Collapse is avoided not by force alone, but by constraint. This is uncertainty acting constructively. The same principle applies throughout atomic structure. Energy levels are quantized. Only certain configurations are allowed. Electrons settle into stable arrangements because anything else would require more energy than the system can provide. The atom finds a balance point, not because it is locked in place, but because alternatives are energetically unfavorable. This balance gives rise to chemistry. Chemical behavior depends on how electrons arrange themselves around nuclei and how those arrangements interact between atoms. Bonds form because shared or exchanged electrons lower the total energy of the system. The shapes of molecules, the strength of materials, and the complexity of biological structures all trace back to these quantum constraints. Without uncertainty, none of this would work. Electrons would not form stable clouds, energy levels would blur into continua, atoms would fail to hold their shape, molecules would never assemble, chemistry would dissolve into chaos, or rather, never arise at all. It is striking how this reverses intuition. Uncertainty is not a source of disorder here. It is the reason order exists. The periodic table itself is a quiet monument to this principle. The repeating patterns of chemical behavior reflect the quantized structure of electron states. Each element differs because of how many electrons it has and how they must arrange themselves within allowed configurations. These patterns are not arbitrary. They are enforced by quantum mechanics with remarkable consistency. This enforcement is gentle rather than rigid. Electrons are not pinned to exact locations. They are allowed to spread, overlap, and interact. That flexibility is what makes bonding possible. Rigid certainty would prevent the subtle sharing of electrons that underlies chemistry. Uncertainty provides room to move without allowing collapse. There is a kind of quiet generosity in this arrangement. The universe permits variability, but within limits. It allows systems to explore possibilities, but constrains them enough to remain stable. The result is a world that is neither frozen nor chaotic, but richly structured. Gentle humour fits naturally here. Nature, it seems, solved the problem of stability not by tightening control, but by refusing to be too precise. By leaving a little wiggle room, it created atoms that endure for billions of years. This perspective also resolves much of the discomfort surrounding indeterminacy. If uncertainty were merely a gap in knowledge, it might feel temporary or unsatisfying, but as a structural feature, it becomes essential. Removing it would not reveal a clearer world. It would destroy the one that exists. Quantum mechanics does not describe a universe constantly on the brink of collapse. It describes one that has found equilibrium through constraint. The same rules that limit precision also limit instability. The same principles that prevent exact trajectories prevent catastrophic failure. Scientific bodies and laboratories have confirmed this picture through countless experiments. Spectroscopy reveals discrete energy levels. Measurements of atomic behavior align precisely with quantum predictions. Chemical reactions proceed exactly as expected when quantum structure is taken into account. The theory does not merely explain why atoms are stable, it predicts how they behave when they interact. This stability extends upward through scales. Solids hold their shape because of atomic bonds. Liquids flow because those bonds allow rearrangement. Gases expand because quantum rules permit wide distributions. Even the rigidity of everyday objects traces back to electron behavior governed by uncertainty. Seen in this way, uncertainty is not something layered on top of an otherwise stable world. It is the foundation upon which stability is built. This reframing also brings coherence to earlier ideas. Probability does not undermine predictability when viewed at the right scale. Uncertainty does not erase structure. Fields do not dissolve objects. Entanglement does not destroy independence at large scales. Each feature that once felt threatening now reveals itself as part of a supportive framework. Atoms do not collapse because the universe forbids exactness where it would be dangerous. It allows precision only where stability can be maintained. The rules are not arbitrary. They're quietly protective. There is something deeply reassuring about this. The same principles that challenge intuition also safeguard existence. The universe is not delicately balanced on the edge of chaos. It is robust precisely because it avoids extremes. It neither freezes everything into rigid certainty, nor allows unbounded variation. Uncertainty in this context becomes a source of resilience. Once this is understood, the earlier discomfort with indeterminacy fades. What seemed like a flaw turns out to be a feature. What felt like a loss of control becomes a gain in coherence. The world does not unravel because outcomes are not predetermined. It holds together because they are constrained. This insight reaches beyond atoms. It suggests a general lesson about how structure arises. Stability does not always come from fixing every detail. Sometimes it comes from limiting how much detail can be fixed. Sometimes order emerges not from exactness, but from the disciplined absence of it. By revealing how uncertainty produces structure, quantum mechanics offers one of its most quietly powerful contributions. It shows that the foundations of reality are not brittle. They are flexible, bounded, and deeply reliable, and in that flexibility lies the reason anything exists at all. Quantum mechanics is often spoken about as if it lives at the edges of reality, tucked away in laboratories and abstract equations, far removed from ordinary life. It can feel like a theory reserved for extremes, for particles moving at enormous speeds or systems chilled close to absolute stillness. And yet quantum rules are woven quietly into the fabric of everyday technology, operating reliably and unnoticed, often billions of times per second. The most striking thing about these technologies is not how strange they are, but how dependable they have become. Consider the transistor. It is difficult to imagine modern life without it. Every smartphone, computer, router, and digital device depends on vast numbers of transistors working together in precise coordination. They switch currents on and off, amplify signals, and perform logical operations with extraordinary consistency. A single modern processor may contain billions of them, each one smaller than a microscopic speck. None of this would be possible without quantum mechanics. Transistors rely on the behavior of electrons in solids, particularly how they move through materials known as semiconductors. Classical physics cannot explain why some materials conduct electricity while others do not, or why adding small amounts of impurities dramatically changes electrical behavior. Quantum mechanics provides the answer by describing how electrons occupy allowed energy bands within a material. In a semiconductor, electrons can exist only at specific energy levels. By carefully controlling these levels through material design, engineers create regions where electrons can flow freely and regions where they are blocked. The transistor works by nudging electrons between these allowed states, using small electrical signals to control much larger currents. This process depends entirely on quantized energy levels and probability-based electron behavior. What matters here is not novelty but reliability. Transistors do not work most of the time. They work essentially all the time. Their behavior is so predictable that engineers design systems assuming failure rates so low they are practically negligible. This confidence comes from quantum theory doing exactly what it says it will do. Lasers offer another clear example. Laser light is not just bright, it is coherent, meaning the light waves are aligned in an exceptionally orderly way. This property allows lasers to cut metal, transmit information through optical fibers, scan barcodes, and perform delicate surgery. The operation of a laser depends on stimulated emission, a process predicted by quantum mechanics. Atoms or molecules are placed into excited energy states. When a photon of the right energy passes by, it triggers the release of another photon with identical properties. Direction, frequency, and phase all match. The result is a cascade of perfectly coordinated light. This behavior cannot be explained without discrete energy levels. Atoms must have well-defined transitions. Photons must carry specific amounts of energy. Probability governs when emission occurs, but the structure of the process ensures that the outcome is highly ordered. Once again, the remarkable feature is not that this works at all, but that it works every time. Lasers operate continuously in factories, hospitals, and communication networks with extraordinary stability. The underlying quantum processes are not delicate curiosities. They are robust enough to be engineered, scaled, and trusted. Medical imaging provides a more subtle illustration. Magnetic resonance imaging, often shortened to MRI, allows detailed images of the interior of the body without surgery. It relies on the quantum properties of atomic nuclei, particularly how they respond to magnetic fields and radio frequency pulses. Nuclei possess intrinsic magnetic behavior that arises from quantum properties. When placed in a strong magnetic field, they align in specific ways. Applying carefully tuned pulses causes them to shift between allowed states. As they return to equilibrium, they emit signals that can be detected and translated into detailed images. This process depends on quantization, probability, and interaction. The signals are weak. The calculations are complex, yet the results are precise enough to distinguish soft tissue from bone, healthy cells from diseased ones. Hospitals rely on these machines daily, confident that the physics beneath them will behave exactly as expected. Behind all of this lies an enormous body of applied research. Universities, engineering institutions, and industrial laboratories have spent decades refining quantum principles into practical tools. This work is rarely dramatic. It involves careful calibration, incremental improvement, and relentless testing. The goal is not to explore philosophical implications, but to make devices that function reliably in real environments. What is striking is how little attention the quantum strangeness itself receives once a technology is mature. Engineers do not worry about wave-particle duality when designing circuits. Doctors do not contemplate probability distributions while reading MRI scans. The quantum rules have been absorbed into the background, trusted implicitly. This trust is earned. Quantum mechanics has been subjected to more experimental verification than almost any other theory in science. Its predictions have been tested across countless systems and conditions. Where it applies with extraordinary accuracy. There's gentle humour in how this contrasts with its reputation. A theory often described as confusing and mysterious underpins some of the most reliable machines ever built. The universe may behave strangely at small scales, but it does so with remarkable consistency. This consistency reinforces an important point. Quantum mechanics is not fragile. It does not fall apart when applied. It does not require constant reinterpretation to function. Once the rules are understood, they can be used confidently. The purpose of grounding abstraction in daily life is not to diminish the wonder of quantum theory, but to place it in context. The same principles that challenge intuition also make modern technology possible. The same uncertainty that unsettles philosophy stabilizes atoms, enables chemistry, and supports complex engineering. Reliability emerges not despite quantum behavior, but because of it. Probability distributions behave predictably in large numbers. Energy levels remain fixed. Interactions follow strict constraints. Engineers build systems that exploit these features rather than fighting them. Scientific bodies and engineering organizations around the world continue to expand this toolkit. Research into quantum materials, precision measurement, and controlled quantum systems pushes technology forward steadily. Much of this progress happens quietly, without fanfare, as ideas move from theory to application to infrastructure. This quiet integration is perhaps quantum mechanics' greatest success. It has moved from a theory that challenged intuition to one that supports daily life without demanding attention. Its strangeness fades into reliability. Its abstraction becomes routine. Seen this way, the journey from atomic uncertainty to everyday technology feels less surprising. Once it's accepted that quantum rules govern matter at its most basic level, it becomes natural that those rules shape everything built from that matter. Computers compute because electrons behave as quantum mechanics predicts. Lasers shine because atoms release energy in quantized steps. Medical images form because nuclei respond to magnetic fields in precise probabilistic ways. None of this is accidental. It is the direct consequence of a theory that describes reality accurately, even when that description feels unfamiliar. By reinforcing theory through application, quantum mechanics reveals its true character. It is not an exotic add-on to physics. It is the foundation upon which much of modern technology rests. And perhaps the most reassuring lesson of all is this: a universe governed by probability, uncertainty and fields is not unreliable. It is dependable in ways that classical intuition never anticipated. The same rules that blur trajectories and soften certainty also power devices that rarely fail. Quantum mechanics does not merely explain the world, it runs it quietly and consistently every day. Quantum mechanics has earned its reputation for reliability. Its predictions have been tested across an enormous range of experiments, from atomic spectra to semiconductor behavior, from lasers to medical imaging. Where it applies with extraordinary precision. It is tempting after such success to imagine it as complete. And yet even the most powerful theories have edges. Quantum mechanics does not explain everything. It was never meant to. Its limits are not failures so much as boundaries, places where the assumptions that make the theory work begin to strain. Recognizing those boundaries is not a weakness of science. It is one of its strengths. One of the clearest limits appears when gravity enters the picture. Quantum mechanics describes matter and energy at very small scales. General relativity describes gravity, spacetime, and the large-scale structure of the universe. Each theory works beautifully in its own domain. Quantum mechanics excels at the microscopic. Relativity excels at the cosmic. Trouble arises when situations demand both at once. Consider environments where enormous mass is packed into extremely small regions, the centers of black holes, the earliest moments of the universe. In these settings, gravity is intense and quantum effects cannot be ignored. Space and time themselves become dynamic, while quantum uncertainty remains unavoidable. Neither theory on its own can fully describe such conditions. Quantum mechanics assumes a fixed background of space and time. Relativity treats space-time as something that bends, stretches, and responds to energy. Trying to apply quantum rules to a geometry that is itself fluctuating leads to mathematical inconsistencies. The equations resist combination. Predictions lose clarity. This mismatch is often referred to as the problem of quantum gravity. It is important to be clear about what this does and does not mean. Quantum mechanics does not suddenly stop working in everyday situations. Atoms remain stable, technologies remain reliable, even strong gravitational fields encountered in most astrophysical settings can be handled using approximations that work extremely well. The breakdown appears only in extreme regimes, far beyond direct experimental reach. At the center of a black hole, densities become so high that classical space-time description breaks down. In the earliest fraction of a second after the universe began, energy densities were so extreme that quantum fluctuations of space-time itself may have dominated behavior. In these regimes, existing theories provide hints, but not complete answers. Physicists have known about this gap for decades. It is not a surprise. It is a signpost. Many approaches have been developed to address it. Some attempt to quantize gravity directly, treating space-time itself as subject to quantum rules. Others suggest that gravity may emerge from deeper structures not yet fully understood. Each approach tackles the same problem from a different angle, searching for a framework that remains consistent where current theories overlap. Large research collaborations across the world are involved in this effort. international teams bring together expertise in particle physics, cosmology, mathematics, and computation. Observatories study black holes and gravitational waves. Particle accelerators probe high-energy interactions. Precision experiments test the limits of existing theories with increasing sensitivity. Despite this effort, no final theory has yet emerged. This is not a failure. It reflects the difficulty of the task. Nature does not reveal its deeper structure easily, especially when the relevant scales are far removed from everyday experience. The history of physics suggests that such transitions take time. Classical mechanics was not replaced overnight. Quantum theory itself emerged gradually, shaped by decades of experiment and debate. There is also a quiet humility built into this moment. Quantum mechanics has not been overthrown. It remains accurate where it applies. Relativity has not been discarded. It continues to describe gravity with stunning success. The challenge lies not in fixing broken theories, but in understanding how two successful descriptions fit together. This perspective matters because it prevents misunderstanding. Limits do not imply error, they imply scope. A map of a city is not wrong because it does not show the entire planet. It is accurate within its intended range. Quantum mechanics is a map of the microscopic world. It becomes less informative when asked to describe the geometry of spacetime itself. That does not diminish its value, it clarifies its role. Gentle humour can help here. Even the most impressive tools have instruction manuals. Quantum mechanics, for all its power, comes with a quiet note in the margins that reads, "Results may vary near singularities." Acknowledging boundaries honestly also stabilizes interpretation debates. Some disagreements about meaning arise from pushing the theory beyond where it was designed to operate. When questions wander into regimes where quantum mechanics and gravity collide, ambiguity is inevitable. The maths itself signals that something new is required. This realization prepares the ground for reflection rather than frustration. Science progresses not by pretending answers exist where they do not, but by recognizing the shape of the unknown. Boundaries guide inquiry. They tell researchers where to look next. It is also worth noting that these limits are extraordinarily remote from daily life. The absence of a complete theory of quantum gravity does not affect chemistry, biology, or technology. The stability of matter remains intact. The predictions of quantum mechanics remain reliable across an enormous range of conditions. The gap appears only when asking questions at the absolute extremes of scale and energy. Questions about the origin of the universe. Questions about the interior of black holes. Questions about whether space and time themselves have quantum structure. These are not practical problems, they are foundational ones. There is something quietly reassuring in this. The universe is not failing to make sense, it is simply more layered than current theories can fully capture. Each layer reveals new structure, while preserving the reliability of the layers above it. This layered view fits naturally with everything encountered so far. Intuition fails at small scales, yet understanding deepens. Uncertainty limits precision, yet stability emerges. Space and time become subtle, yet experience remains coherent. Boundaries appear, not as dead ends, but as invitations. Scientific institutions continue to approach these questions with care. The language used is cautious, claims are restrained. Progress is measured not in dramatic announcements, but in improved consistency, refined maths, and clearer connections between ideas. This restraint is intentional. History has shown that rushing conclusions in foundational physics rarely ends well. The universe rewards patience. By acknowledging where quantum theory stops working, the narrative shifts gently from explanation to reflection. It becomes possible to appreciate how much has been understood without demanding immediate closure. The unknown is framed not as a gap to be filled hastily, but as a horizon to be approached thoughtfully. This honesty also reinforces trust. A theory that openly acknowledges its limits is more reliable than one that claims completeness prematurely. Quantum mechanics has earned confidence precisely because it makes clear statements about where it applies and remains silent where it does not. As the exploration nears its closing stages, this perspective becomes increasingly important. Understanding does not require final answers to every question. It requires clarity about what is known, what is unknown, and why the distinction matters. Quantum mechanics stops working not because it fails, but because reality continues beyond its current reach. That continuation is not a threat to coherence. It is a reminder that science is an ongoing process, one that advances by respecting both its achievements and its boundaries. In recognizing where the theory ends, a quieter insight emerges. Knowledge is not diminished by acknowledging limits, it is strengthened. And within those limits, quantum mechanics remains one of the most reliable guides ever developed, even as it points calmly toward questions still waiting for their turn to be answered. Ignorance usually carries a negative weight. To admit not knowing can feel like weakness, hesitation, or failure. In everyday settings, uncertainty is something to be resolved quickly, smoothed over, or hidden behind confidence. Science, however, treats ignorance very differently. It treats it as a signal, a marker, often as an invitation. Some of the most important advances in physics began not with answers, but with discomfort. Observations that did not fit expectations, measurements that refused to align with trusted models, results that felt wrong, not because the data were flawed, but because the ideas used to interpret them were no longer sufficient. This pattern appears again and again. At the end of the 19th century, physics was widely regarded as nearly complete. The laws of motion were known. Electromagnetism had been unified. Many believed that only small refinements remained, and yet experimental puzzles were quietly accumulating. Heat radiation behaved oddly. Atomic spectra showed unexplained lines. Light produced effects no one could account for. These were not dramatic mysteries. They were technical irritations, minor inconsistencies that refused to disappear. Rather than ignoring them, physicists leaned into the confusion. They treated the mismatch between theory and experiment not as an embarrassment, but as a clue. That willingness to sit with uncertainty allowed something new to emerge. Quantum mechanics did not arise because everything made sense. It arose because something clearly did not. The same is true throughout the history of science. Classical mechanics worked brilliantly until it didn't. Newton's laws described motion with extraordinary accuracy, yet subtle discrepancies accumulated in planetary orbits. Those discrepancies did not invalidate the theory. They revealed its limits. From that revelation came a deeper understanding of gravity. Ignorance, in this sense, is not a void. It is structured. It has shape. It points toward where existing ideas are stretched too thin. What distinguishes science from guesswork is how this ignorance is handled. It is not filled with speculation for its own sake. It is not ignored in the hope that it will go away. It is documented, tested, and revisited. Questions are sharpened rather than blurred. Assumptions are examined rather than defended. This requires humility. Humility in science does not mean doubting everything or refusing to commit to conclusions. It means recognizing that even the best theories are provisional. They are maps, not territory. They describe reality within a certain range, and outside that range their guidance fades. Quantum mechanics exemplifies this attitude. It makes extraordinarily precise predictions where it applies. At the same time, it openly acknowledges where it cannot yet speak. It does not pretend to explain the origin of spacetime or the deepest structure of gravity. It leaves those questions open, not as failures, but as boundaries. This openness is not passive, it drives research. Entire fields of physics exist because someone was willing to say, "This does not quite work." Particle accelerators were built to explore gaps in understanding. Space telescopes were launched to probe anomalies in cosmic behavior. Precision experiments were designed to test assumptions thought to be settled. Each of these efforts began with uncertainty. There is a temptation to think of scientific progress as a steady march toward complete knowledge. In practice, it looks more like a series of adjustments. Periods of clarity are followed by moments of confusion. Each time confusion appears, it marks the edge of a framework that has done its job. Seen this way, not knowing is not an obstacle to progress. It is its engine. Gentle humour helps here. If science only advanced when everyone felt confident, it would have stopped centuries ago. Progress depends on a certain tolerance for being wrong, or at least incomplete. The universe rarely rewards certainty with new insight. It responds better to careful doubt. This perspective also stabilizes the emotional experience of open questions. It is easy to feel unsettled by the idea that fundamental aspects of reality remain unexplained. What is time, really? Why does gravity resist quantization? What lies beyond current theories? These questions can feel like loose ends. Science treats them differently. Open questions are not loose ends. They are guideposts. They help prioritize effort. They shape experiments. They encourage collaboration across disciplines. They prevent stagnation by reminding researchers that understanding is always in progress. Importantly, this does not mean that everything is uncertain. Much is known with extraordinary confidence. The stability of atoms, the behavior of electrons in materials, the rules governing chemical reactions. These foundations are not shaken by unanswered questions at deeper levels. Ignorance coexists with knowledge. The two are not opposites. They define one another. This coexistence is one of science's quiet strengths. It allows confidence without arrogance, precision without finality. Theories are trusted where they work and questioned where they do not. Historically, the moments when science advanced most dramatically were often those when ignorance was faced directly rather than avoided, when unexpected results were published rather than dismissed, when confusion was treated as meaningful rather than inconvenient. This attitude is not limited to physics. It appears throughout scientific practice. In medicine, unexplained symptoms drive discovery. In biology, anomalies lead to new understanding of life's complexity. In climate science, uncertainties guide the development of better models. In every case, ignorance functions as a tool. It narrows attention. It sharpens questions. It motivates careful measurement. Without it, science would become a catalogue of accepted facts, disconnected from discovery. There is also a deeper philosophical comfort in this approach. It acknowledges that the universe does not owe complete transparency. Understanding unfolds gradually, shaped by what can be measured and tested at a given time. Expecting total clarity is not a scientific requirement, it is a human preference. Quantum mechanics has repeatedly taught this lesson. Each time intuition failed, deeper structure emerged. Each time certainty dissolved, stability was found at a new level. Uncertainty did not signal collapse, it signaled transition. By reframing ignorance as progress rather than deficiency, the narrative changes. Open questions no longer feel like gaps in reality. They feel like the next steps in a process that has always moved forward by questioning itself. This reframing also invites patience. Some problems take decades. Others may take centuries. Some may require entirely new ways of thinking. Science is comfortable with that timescale. It is not in a hurry. The purpose here is not to romanticize confusion, but to normalize it. Confusion is not the enemy of understanding. It is often its starting point. As the exploration draws closer to its end, this perspective becomes especially valuable. The absence of final answers does not diminish what has been learned. It contextualizes it. It reminds us that knowledge grows by expanding into the unknown, not by pretending the unknown is smaller than it is. Ignorance, handled carefully, becomes one of the most powerful tools science possesses. It keeps inquiry honest, it keeps curiosity alive, and it ensures that progress remains possible, even when certainty feels out of reach. In that sense, not knowing is not a flaw in the scientific story. It is one of its defining features. Standing at the edge of quantum understanding does not feel like standing before a void. It feels more like pausing at a shoreline, where familiar ground gives way to deeper water, and where the surface remains calm even as unseen structures extend below. After following quantum ideas through uncertainty, probability, fields, entanglement, and limits, what remains most striking is not how unstable reality becomes, but how reliably it holds together. Again and again, quantum mechanics has shown that while intuition may falter, structure does not. Measurements produce consistent outcomes, predictions align with experiment. Technologies built on quantum principles function with extraordinary dependability. Whatever reality may be doing beneath the surface, it does so with discipline. This reliability is easy to overlook amid discussions of interpretation and mystery. It is tempting to focus on what is unresolved, on questions that remain open, or descriptions that feel incomplete. Yet every experiment ever performed within the domain of quantum mechanics has returned results that fit the same underlying framework. The theory does not wobble when interpretations diverge. It does not depend on agreement about meaning to function correctly. Measurement sits at the heart of this stability. When quantum systems interact with the world, outcomes appear, detectors register events, records form. These processes are not vague or ambiguous. They are repeatable physical interactions that behave the same way every time the same conditions are prepared. Whatever philosophical story is told around them, the measurements themselves remain firm. This is an important anchor. It means that reality does not change depending on how it is interpreted. Whether one prefers to think in terms of collapse, branching, guidance, or contextual properties, the observable world remains the same. A photon is detected. An electron leaves a trace. An atom emits light at a specific frequency. Interpretation reshapes understanding, not outcome. This separation is quietly reassuring. It suggests that the universe is not waiting for consensus before behaving properly. It follows its rules regardless of how they are described. Human frameworks adjust. Reality does not. Earlier discomfort with uncertainty often stems from the fear that lack of certainty implies lack of structure. Quantum mechanics demonstrates the opposite. Uncertainty limits what can be defined simultaneously, but it does so in a precise way. Probability governs outcomes, but it does so with exact distributions. Fields fluctuate, but within strict constraints. Even the vacuum behaves according to rules that can be measured and tested. Standing here, it becomes clear that quantum theory is not a story about instability. It is a story about limits that protect coherence, about rules that allow variation without collapse, about a universe that resists being pinned down too tightly, yet never drifts into chaos. The diversity of interpretations reflects this resilience rather than undermining it. Different conceptual lenses can coexist because the mathematical structure beneath them is solid. The equations do not argue among themselves. They produce results. The debates arise only when human language tries to describe what the equations imply beyond what can be measured. There is a quiet humility in accepting this. It allows understanding to remain open without becoming anxious. Not every question needs an immediate answer. Not every gap signals failure. Some gaps simply mark where language, imagery, or intuition have reached their limit for now. This openness is not passive. It has always driven progress. Each time quantum mechanics revealed something counterintuitive, it did so through careful experiment. Each time confusion arose, it pointed toward deeper structure rather than emptiness. The pattern suggests that what lies beyond current understanding is unlikely to be arbitrary or chaotic. It will likely be constrained, consistent, and precise in ways that are not yet visible. Standing at the quantum edge also highlights how much has already been learned. Matter is not solid in the way it appears, yet it is stable. Energy is discrete, yet it flows smoothly at large scales. Light does not fit a single category, yet it behaves reliably. Space and time grow subtle at extreme scales, yet everyday experience remains coherent. Even emptiness turns out to be structured. None of this diminishes the world, it enriches it. Gentle humour finds its place here as well. The universe, for all its complexity, seems remarkably patient with misunderstanding. It allows humans to use simplified models where they work, and it reveals deeper layers only when pushed carefully by experiment. It does not demand immediate comprehension. It waits. What matters most at this edge is not arriving at final answers, but recognizing how understanding evolves. Physics has never advanced by closing questions prematurely. It advances by learning which questions can be answered precisely, which must be reframed, and which are best held open for now. Reality remains stable throughout this process. Atoms do not flicker out of existence because interpretations differ. Technologies do not fail because debates continue. The moon does not vanish when unobserved, nor does light refuse to behave when no one is watching. The universe continues to operate according to rules that have proven extraordinarily robust. This stability allows curiosity to be gentle rather than urgent. There is no need to force resolution. The quantum world does not ask to be solved in a single sweep. It invites careful attention, repeated testing, and patient revision of assumptions. Standing here, the arc of the journey becomes clear. Intuition was challenged, not discarded. Certainty was softened, not destroyed. Objects gave way to processes. Independence gave way to relationship. Determinism gave way to probability. At each step, something familiar was loosened, and something deeper took its place. What remains unresolved is not a failure of understanding, but its frontier. The edge of quantum theory is not a wall. It is a boundary shaped by current tools, current questions, and current language. Beyond it lies further structure, still hidden, still forming, still consistent with everything that has already been confirmed. Closing without finality means allowing that boundary to remain visible. It means resisting the urge to declare completion where none exists. It means recognizing that knowledge can be strong without being total. In this sense, standing at the quantum edge is not an ending. It is a pause, a moment to look back at how much coherence has emerged from what once seemed strange, and to look forward without urgency to what remains to be understood. The universe does not demand certainty to function. It does not require final explanations to remain stable. It simply continues, governed by rules that are precise enough to build worlds and flexible enough to surprise those who study them. And so understanding remains open. Not unresolved in a troubling way, but unfinished in a productive one. The quantum edge holds firm beneath the feet, even as it stretches onward into deeper questions, inviting continued exploration without ever threatening the quiet reliability that has carried everything this far. Quantum theory often arrives wrapped in language of mystery. as if it describes a world that slips away the closer it is examined. And yet, after tracing its ideas carefully, what stands out is not how much reality dissolves, but how much of it remains intact. The deeper the theory reaches, the more clearly it reveals a boundary. Not a boundary of chaos or confusion, but a boundary of meaning. Quantum mechanics does not tell everything it never promised to. What it does provide is a remarkably precise account of how nature behaves within a defined domain. Within that domain, physical law does not weaken or fragment. It becomes more disciplined. Measurements remain reliable. Structures remain stable. Predictions remain consistent. The continuity of physical law is not lost as understanding deepens. It is refined. This continuity is easy to miss when attention is drawn toward what cannot yet be answered. Questions about interpretation, about time, about gravity, about what lies beneath current descriptions can feel unsettling. But these open questions do not float in isolation. They rest on a foundation that has proven itself again and again. Atoms behave, chemistry works, technology functions. The world does not flicker or fail simply because its deepest description is incomplete. Quantum theory marks a boundary not because reality stops making sense, but because certain kinds of sense stop being available. Classical intuition reaches its limit. Everyday categories lose their usefulness. Exact trajectories dissolve into probabilities. Objects blur into interactions. What replaces them is not absence, but structure of a different kind. This boundary is not unique to quantum physics. It appears whenever understanding advances far enough to outgrow its original language. Space and time once felt absolute until relativity reframed them. Matter once felt solid until atomic structure revealed its openness. Each time, meaning shifted without breaking continuity. The laws remained. The descriptions evolved. Seen this way, quantum mechanics is not a theory of confusion. It is a theory that clearly signals where explanation must change its form. It tells what can be calculated and measured with extraordinary accuracy, and it remains silent where questions exceed what current concepts can support. That silence is not weakness, it is discipline. There is something deeply stabilizing in this. A universe that admits mystery without surrendering reliability is not fragile. It is resilient. It allows understanding to grow without demanding finality. It supports precise knowledge where precision is possible, and it leaves space where new ideas may one day take shape. Mystery in this context does not erode reality. It deepens it. Knowing that the vacuum is active does not make space feel emptier. It makes it richer. Knowing that uncertainty underpins stability does not make matter feel less real. It makes its persistence more remarkable. Knowing that interpretations differ does not weaken physical law. It highlights how strongly that law holds beneath varied descriptions. Quantum theory teaches that meaning is not always found in definitive pictures. Sometimes it emerges from limits, from knowing what cannot be asked cleanly, from recognizing where language reaches its edge. These limits do not block understanding, they shape it. This shaping is gentle rather than dramatic. There is no sudden loss of coherence at the quantum scale. There is no collapse of order. What appears instead is a steady handoff from familiar intuition to careful structure. Reality continues to behave consistently even as explanation becomes more abstract. Ending without resolution does not mean ending without reassurance. The absence of final answers does not imply instability or incompleteness in the world itself. It reflects the nature of inquiry, not the fragility of existence. The universe does not wait for explanation to function. It functions first, and explanation follows where it can. Quantum mechanics, at its boundary, leaves understanding open in a way that is calm rather than troubling. It invites patience. It allows questions to remain active without becoming urgent. It suggests that knowledge can be strong without being total, and that coherence does not require closure. The laws of physics do not flicker at the edge of understanding. They continue smoothly, governing interactions, structures, and change with quiet consistency. What shifts is perspective. What changes is the way meaning is drawn from behaviour. In that sense, quantum theory does not pull the ground away beneath reality. It reveals how firm that ground is, even when its deepest layers remain unseen. It shows that mystery is not a crack in the foundation, but part of its design. So the journey does not end with an answer. It settles instead into a view. One where reality is stable, law is continuous, and understanding is allowed to remain unfinished. One where the unknown is not a threat, but a horizon. And at that horizon there is no urgency, only space to pause, to reflect, and to recognize that the universe, even at its most elusive, remains quietly, reliably itself.